Next. I don't first one.
Hi, good morning.
Hello, hello,
Okay, welcome.
welcome.
Stay on the line. You will let
Okay.
you know when the time is right. Thanks.
Can you hear me?
Yes, we can.
Okay, okay.
Okay.
Hello, hello.
Hi.
I would like to upload my presentation material right now.
Yes, please stay on the line. We are busy with the preparation. You will be given opportunity.
Okay.
Yes, welcome. Stay on the line.
It's not active. It's not active.
Hi, doctor. The schedule is we're starting at 8:55, so another 2 minutes or so.
It's okay. My presentation is you can see.
Yes, we can. You can see your
Okay,
screen.
okay. Yo, you able to see my cursor, mouse cursor? You can see you
We can
are able to
see you,
identify.
we can hear you.
Okay. Mouse cursor, you are see? You can see?
Yes, I can see your screen.
Okay.
Yes, welcome.
Should I do a test as well for the presentation?
Yes.
Could you please open the permission for me? I have still the message, there's no permission to open.
Colleagues, can we get started with this morning session? Good morning. My name is Chachi Chibane. Thanks for gracing us with your presence again this morning to come and discuss the neutrons and the source that we are anticipating in the near future. House rules first. There is an assembly point in case of anything that happens. We hope there is nothing that is parking lot. And then the bathrooms are around the corner. You go out to your right and you turn right again. You'll see them. And then the tea break will be served outside at the foyer. It's on your left and on your right. I think those are the house rules that I wanted to share with you. I also want to welcome the colleagues that have joined us online. We're hoping we are going to build a user community from this workshop, which is what the aim of this workshop is all about. Yesterday, we had several talks regarding the neutrons. Neutrons are not necessarily competing with X-rays or the electrons, but they are just complementary. And because we like, and for the fact that they are uncharged, they can be particles, they can be waves, they've got magnetic moment, and so they can actually investigate bulk materials. And the one advantage with these neutrons is if you look at other techniques whereby the interaction is with the electron cloud, as you add the electrons, you might not necessarily be able to see the different isotopes. However, the neutrons are so erratic such that you can actually see, you can actually differentiate between an isotope of hydrogen being that of deuterium. This is one of the techniques that I think we spoke about thing in the neutron scattering techniques. The other good thing about them their energies. We can condition them to very low energies such that they have got long wavelengths. And then with that, you can actually investigate
to show your
those tissue
presentation?
samples, your biological samples that you don't want to damage with other techniques. We are not saying other techniques must be ruled out.
Chair?
They are complementary, they are not competing. Unfortunately, you cannot have a neutron source in your backyard like you will have with your X-ray source. That's the only disadvantage. That's why we are here. We are going to build the beam lines according to our needs as the South African community, and in particular, and Africa and the rest of the world. With those few words, I would like to welcome our dignitaries, the executive from NEXA, executive from DMRE, and
Dr. Chair,
PSI.
can you please share your presentation?
We are glad in our lifetime we have got this opportunity, and
Please say something so
the
that we
support
can see
from
you're
those
connected.
stakeholders. And I also want to thank you to be part of this mega project. In those ways,
Say something, Dr.
welcome.
Chair.
To this first session, the last day of the workshop, and I would like to introduce our speaker who will open this session. Is Dr. Musim. Dr. Musim is actually a scientific advisor at Korea Atomic Energy Research Institute.
Can you please share your
which is known as
presentation,
KAIRI,
Dr. Chair?
Neutron Science Center in Korea, in South Korea. He's an electronic engineer by qualifications. He obtained his PhD in 1988, and then he extended his work in the field of agricultural research, whereby he was using electron beam and neutron imaging techniques. He was actually involved in establishing a neutron imaging facility at Hanaro, a high flux advanced neutron application reactor. And he has experience in a number of diverse fields and is involved in numerous collaborations, which include development of energy fuels, neutron detectors, ultrasonic systems, fast neutron interrogation system, as well as the aircraft neutron radiography inspection systems. Please help me to welcome Dr. Sim.
Hello, Secretary. Can you hear me? Can you hear me? Hello? Can you hear me?
Yes, we can hear you. Welcome.
Okay. Good morning. Korea is good afternoon. Okay. It's a time delay is 7 hours. I am very delightful to be with you in occasion of SA-SENS2022 workshop. First of all, so thank you for having me, Professor Andrew and Dr. Robert. First, Dr. Robert. Mr. Robert, I meet you. Raise your hand. Thanks. 2 weeks ago, I was in Manila, Philippines, to attend IA meeting. I heard the Christmas carol song the first time of this year. This time, I would like to greet you Christmas in advance. I would say, everybody, South Africa, South Korea, Merry Christmas. Okay. Before I get into my titles, water quantification measurement loop to in soil, I tell you a review of a perspective of a neutron imaging of agriculture. I briefly tell you what I am doing talking. I would like to address big issue. The reason we have to be dragging, kicking, screaming for the agriculture development. I will review what we have done so far with the World Conference on Mutual Radiography Proceeding and the International Journal articles. Finally, I would like to share carry experimental and result and sweat experience. And finally,
Can you share the
I-
presentation, please? Can you please share your presentation?
Yes, I go on. Why?
Can you please share your screen, the presentation? We are not able to see your presentation, Dr. Mo.
Okay, so unfortunately.
Yes.
Oh. I start. Can you hear me? Yeah.
We can hear you.
Yeah. My figure is up here? No,
Not yet.
not yet. Oh, unfortunately. I uploaded it already.
If you go to share screen
Yes.
on the bottom, just next to the taskbar, there's a share button, share screen button there.
Yes. Share working.
Share screen button.
Yesterday, successfully, my presentation up here. Why?
One short comment. If I try to open a presentation, there's the information that there's no permission from the host to open the screen.
Okay. Would you open the co-host to me? It's appear non-active. It's sharing presentation not active.
Then can you please try again, Dr. Sim? We just did something on our side here. Can you please try to share again?
Now it works in my case.
Okay. So, okay.
Yes, thank you very much. It's okay.
Yeah.
Now you can continue.
Okay. Go ahead.
Then go ahead.
Okay. Can you hear me?
Okay.
Let's start.
We have your presentation. We can hear you. Please continue.
Okay. I am very good morning. Good morning. This Korea is good afternoon. I'm very delightful to be with you in occasion of the SA-SENS2022 workshop. First of all, thank you for having me, Professor Andrew and Dr. Robert. There's Mr. Robert. I miss you. Raise your hand. Okay. 2 years ago, I was in Manila, Philippines to attend IA meeting. I heard Christmas Carol song the first time of this year, I would like to greet you Christmas in advance. I would say everybody in South Africa, South Korea, Merry Christmas. Before I get into my title, water contribution measurement in root, plant in the soil, I tell you, review and perspective of the nutrient for agriculture. I briefly tell you what I would like to address the issue. The reason we have to this dragging, kicking, spring for agriculture development. I'll review what I have done so far with the World Conference, nutrient radiography proceeding, and the international journal articles. And finally, I would like to share the carry experimental result and SWAT experience. Finally, I would like to share, I give you hopefully perspective of contributing nutrient imaging to breaking agriculture technology. Let's go in background. Population explosion, climate changes caused the food crisis. In 2022, estimated 7.5 billion. You know, about 1 billion people are suffer from the food shortage. By 2050, it is expected there will be 10 million people. Then about 20% people are expected to face food poverty. And climate changes, aggravated water shortages, submerged field, and temperature is expected to increase 2 degrees by 2 degrees Celsius by 2050. And climate change, high temperature melting Himalaya range glaciers make melting. In China, Yellow rivers, Yangtze rivers, Mekong river dry. And these areas, rice paddy, huge rice paddy zone. And climate change and submerged East Asia, East South Asia, and Pacific Island, and Sri Lanka and Bangladesh. And the climate change aggravates the food crisis. We are back to the 18th and 19th century of food crisis and 20th century of agricultural technology innovation. You know, Maldesian series of population, he said, arithmetic food supply growth and exponential population growth. He said, 1 million people can survive on the earth. At the time, the Maldesianist against bill of limited poverty. After 4 years, huge starvation engulfing Scottish and Irish. They are immigrants in the United States, and they found us McDonald's. McDonald's feed my kid occasionally. And you know, Harvard, 20th century agricultural technology innovation. Harvard invented artificial nitrogen fixation. And his invention, bright demographer Meldorf Fripp. At the time, Meldorf's labor images technology progress is definitely that of the technology innovation. And power invention can feed the Earth people in the 20th century. But unfortunately, now 1 million people are faced with food shortage. In 2050, more of the way, there will be about 2 billion people who are expected to face starvation. According to United Nations report 2019, food production should increase by 70% to support the future population. Which is technical crew for struggling with the issues of food crisis. Think over we all together, ponder over. Technical crew, what is technical crew? We are together thinking over. Many people in this stage, everyone gets to know this fabulous production of smart vertical farming. Smart vertical farming, Professor Dixon Despomiers is revealed this idea. He designed the concept, designed this 48 flower smart vertical farming beside 60 hectares. Its crops are high likely capable of feeding 50,000 people. It started urban farming. This application, current application, smart vertical farming is coupled with other states art technology, have resulted in 10 times crop yield other than a traditional farming method. And surprisingly, good news, consuming energy less 40% energy usage and 80% less food waste. That's why we are very well cultivate, well store, well control, and 80% less water usage than in traditional farming method, according to Japan company Mirai. Yes. Smart vertical farming coupled with the state-of-the-art technology is capable of feeding the 20th century. What is coupled with other state-of-the-art technology? Definitely. You definitely know the word of the AI and robotics, drone, IoT is a highly repugnant like a virus. Those technologies need much more bunch of brains for enhancing its integrity, sustainability. We mean the much brain is much data. Data is crucial. Big data farming. Soil moisture, temperature, infrared image, high spectral image, carbon dioxide, plant nutrition, organic mineral. This data is very touchable. But water irrigation. Water, water is the essence of nature. Water irrigation in plant. Only nutrient gives us a comprehension, understand, figure it out how to channeling, how to watering nutrient into many units, very costly, very limited, very precious for figuring out. the life of the plant is coupled with the state-of-art technology. Now start nutrient imaging is emerging technology. You have to see the figure. Yes, nutrient imaging on the movement toward through the plant. Nutrient image modalities feature of significant advantage. Animal, X-ray microsheeting, and animal is magnetic property interference soil. It does not give a sense. Truly, X-ray microsheet is only morphology, not sensitivity to water. And you know the GPR techniques, the non-destructive test is determine what amount root plant in shallow soil. It is practically unlikely to carry out in situ a root plant in soil. Nutrient imaging is palatable technique to determine water content concentration in soil as well as root growth, root water taking. You keep in mind, and there are several questions. Is applicable, not field. More smart vertical farming, only cultivation protection, not applicable to field. Very nutrient is so limited, so costly. And experimental, only seedling and germination and pollination, culturing in protect cultivation of smart farming facility, hydroponics, aquaponics, aeroponics, soil ponics. You see, in Switzerland and the PSI nutrient imaging facility, there are propounders and the water distribution around the plant root. You know, nutrient imaging facility in the PSI. You know how many people work there? Don't surprise. 26 people work there, nutrient imaging only. I will review. I'll give insight. What we would like to do. We are back in 1980, 1990. We have to reflect some experience. Firstly, experimental. And this nutrient radiography shows how the root emergency and root development. At the time, very anxiety. And then second one is the second experimental, what kind of soil medium is more appropriate for soybean cultivation? They would assess what kind of mixture. Very important. And in 1990 and 2000s, we back. They nutrient image. What this imaging study water movement near the root as plant grows, water uptaking along was relatively high along the upper part root where the secondary root was developed. And these images found that the damage of water loss from the small defect of surface leaf. The first, they are able to measure the deduced ballast of the water uptaking the tomato seedling. Very meaningful. And the city first experimental. Many of the anatomical features of the corn kernel. This could be identified. The difference found is inoculate, not oculate. is subsector color. The first experimental CT imaging. And they are combined MRI neutron more sensitive than MRI. And they are, second one, they are 3D visualization. Deep 2O testament across, they are visualized in the pathway, cell pathway, apoptotic and cell pathway, how to pass the water. This figure is in the xylem and these pathways, apoptotic and the cells pathway. In journal, we get a journal article 2016. Yeah, and they are quantitative imaging infiltration root growth. Infiltration uptake of water is modified by plant root more rather than effective stem, seed, and soil structure and moisture. Yeah, that's a surprising result. You see, after irrigation, the water is dry, and 6 days after irrigation, and plant feel the drought, face drought, in order to B10. They emit lipid mercenage to keep more water. It's like a lipid stick. It's so-called mercenage. And 6 days after, water pour them, and they cannot drink. This area is dry. I'll give you a tip. When you go to the long trip from the home and 1 week and come back home, you feel guilty of plant, and pour them water, and then water does not adjust to much of water, and you careful little bit water to pour them or water them. And this 3D imaging observers a true loose surface and operate the user assumption. And even there's visualization, embolism, formation. This embolism is called human beings like cancer. In order to cure embolism, it is necessary to visualize how to treat embolism. And it's real time water distribution and ventilation network, self-flowing leaves, and transpiration real time, and respond to environment condition and plant water stress. Yeah, in real time. Imaging, dynamic monitoring, in viewing convection, drying tunnel. They assess the impact of several process conditions or evaluate, and including airflow, temperature, airspeed, and instant radiation. Yeah, this is they would like to assess and mineral mixture, zinc distribution, and the last, the other one is phosphorus and zinc distribution. How affected our growth, plant growth. 10 minutes left. Okay. Chairman. Chairman. How many minutes left?
Hello?
How many minutes left? 10 minutes?
Hello?
Hello? 10 minutes left?
How many laps?
Yeah. Oh, no, I wasn't connected. Sorry about that.
Okay.
Your session is all the way up till at 9:45. So
Okay.
we're still having
Okay.
15 minutes.
Let's go. Let's go. Yeah. I will show you the core activity and neutral image of plant. It's very interesting. We can result. The first experimental result with collaborative weapons. We are at the investigate how to wither it. The cut flowers. Cut flowers growing is lunar side, and we have to transport the lunar from the ovens. This takes 3 days to 4 days. We keep the fresh. We have to treat the chemical to keep them fresh. And we are studying like this. And this laptop in very interesting result and interactive ionic concentration and potassium over the calcium concentration relation can dynamically actively regulate water transport, and the xylem is regulate depend on the concentration ratio and potassium over calcium ratio. In potassium over calcium ratio 100 is actively regulate and xylem, and the other side 1:0:1 point ratio potassium over to calcium is slowly regulate to adopt the invited change. I do the experiment carry, and we spend the experimental. It's long story. We spent more than 10 years to develop this project. We formatted 4 fields. One field was formatted by using soil after harvest, and second field was formatted by the pesticide fumigation soil. The third field was formatted by electron beam treatment soil. And the last one is formatted in virgin soil, and we embedded the many aluminum pots planted in root in aluminum pot for scanning neutron cities periodically. See, and this site, and periodically bring us a port and scan the port, the ginseng port. And we are able to see the root images like the 0.3 millisize with resolution, and we are able to see health, all the root, four-year root, and rotten root, and lusty root. We are able to see. Tell the symptom, and we are the separated root and segmented, and the soil. This result with publications in the scientific report. There are many institutions involved in this project, and 12 institutions and universities, and 19 research involved in this project. At the time, we are given many questions. They are wondering if CT image is able to measure water content even 30 millimeter. In order to respond with the answer, they wonder, we have to do simulation, math stuff. Conducted by Mr. Robert. Surprisingly, with penetration ratio exceeds 32%, and even soil moisture 12. We are calculating penetration ratio. We are able to see measure water content. This actually, I'm in fact filled with water embedded in soil moistures 1, 2, respectively 10. And for setting up the calibration, water content measurement. Then we establish calculate curve, water content and penetration ratio to measure water content in the soil. Root in soil. And firstly, using the histogram allow us to figure it out water content, figuratively, quantitatively, root volume. Like this, root volume and water content, quantitative water content. Like this. Based on calibration, water content measure of the calibration in root. Based on this calibration curve, we are able to measure water content quantification. This area is the moistures is 7.7. We have to measure water content approximately, and this area approximately 55 and 70. We are measuring based on calibration curve, and this fourth experimental result will be published soon. Prospective nutrient imaging tools to visualize water behavior and root morphology. And we have many challenges. And I study provide us comprehension of take water in leisure sphere. So how to activate and burn, pass down, and east. And you see, and I study provide expert evidence. 10 years, 20 years ago, and some scientists experiment how to xylem modulate. They used the tube instead of nutrient imaging. Is provide experiment instead of challenge nutrient imaging. And you left for science and 21 like this, and depends on concentration
Sorry, Dr.
ratio.
Sim.
Okay.
Sorry. You've got 5 more minutes, but that will include question session.
Okay,
if you can just wrap up so that we can follow up with
some questions.
questions.
And nutrient image also visualizes more in the depends on the type of condition of soil. You are able to visualization. Even you can see depends on the different photo sensor system. Wavelengths depend. Wavelengths is due to its shape different. Like this. This gives us a nutrient imaging challenge. Yes, nutrient hydrology. ledger-spheres and xylem leaves are largely uncharacterized at present. Application dynamic neutron imaging shows great promise for addressing many of the challenging questions related to plant hydraulic behaving, then while doing vertical smart farming for serving with food shortage. Okay. I'll show. Next is during the discussion, I did this for the computer tomography, and then I'd like to recommend NASA to build a hybrid neutron X-ray CT center, and you establish 10 units. It's in a Korea situation. It's computer tomography very happy. Welcome World Conference non-disk testing 2024 in Incheon, Korea, May 27 and 31. Thank you for having me. Okay.
Thanks very much. I'll allow the floor for the questions. Please, colleague, also check on the charts if there are any. There is one question.
So I find this neutron imaging approach very interesting, but I'm just curious. It seems to be very expensive. You know, how much would it cost to apply it maybe on a 40-story? No, I find the neutron imaging approach very interesting, but it appears that it would be very pricey to actually implement it. So
Yes.
I heard that it's actually viable for vertical farming. So now my question would be, maybe on a 48-story building that is about a hectare, how much
Yes,
would it cost? You know,
how much cost?
how
One-
much would it cost?
$100 million.
All right, thank you.
48 this smart vertical farming, and first investment very price, and
Wow.
and accommodate 500,000 people
Mhm.
and affordable.
Wow,
You know-
that was my earlier comment. Thanks, Dr. Sim. That was my earlier comment regarding not having to be able to own a neutron source in the backyard.
Yes.
I think you mentioned something about the expensiveness of the neutrons in one of your slides. Yeah. One more question. There is one there.
Great. Thanks very much for the presentation.
Okay.
Your work has focused on water uptake and so on. What I want to know is there a possibility of looking at nutrient uptake as dissolved solutes? Have you thought about that? Is that going to be a possibility? Thanks.
Yes.
Yes, Dr. Sim?
Yes.
You will be able to investigate the take-up of nutrients in your plants.
Yes. You know, the nutrients means and potassium and the calcium is concentration ratio. Concentration ratio is depends on the velocity is different. I showed the previous is concentration nutrient in the uptaking velocity is different, very variant. To capitalize what's nutrient in the water.
All right. No,
Okay.
thanks very much.
Okay.
I don't see any more hand. Then we can move to we can thank the speaker and move to the next one. Our next speaker is Dr. Ralph Gills. He's the head of advanced materials at FRM2 in Germany. Dr. Gillis is a physicist by qualifications with a PhD, and he has a research group called Advanced Materials with expertise in neutron scattering methods for studying energy materials as high temperature alloys and batteries. At the FRM2 research reactor, he worked as an instrument scientist to design, build, and brought into commission the structure powder diffractometer, as well as the small angle neutron scattering instrument. And then in his group methods as diffraction, small angle scattering, imaging neutrons, neutron depth profiling, neutron induced prompt gamma activation analysis are applied mainly on alloys and battery research. He has authored over 170 public peer-reviewed articles, whereby almost 40 of them he was the main author or the primary author, on topics ranging from instrumentations at large-scale facilities, alloys development, thin films, ceramics over to in situ and operando studies of batteries. Furthermore, he's also involved in industry as a coordinator in the use of the scientific instruments at FRM2 or MLZ. The engineering application using neutron scattering. Welcome, Dr. Gillis. Thank you.
Rosit, South Africa. So thank you, Mr. Chairman, for your kind introduction. Welcome you all. And first of all, I would like to thank the organizers to invite me for this talk. So my topic and focus are the engineering applications, and they are really strongly related to industry. So I'm from the FRM2, which started 2004 with 25 instruments now. Before we were at the atomic egg, which was in operation from the 50s to 2000, the first nuclear facility in Germany. So we are located north of Munich, close to the famous soccer club Bayern Munich, and we are connected with subway close to the city of Munich. And there's a huge campus, which is also good for students, with many institutes, and we have a lot of partners which are located nearby. What is particular at our facility at the Heinz-Meyer-Leibniz-Zentrum FRM2 is that we have only one fuel element in the center, and this one has 8 kilogram weight and produces 8 times 10 to the power 14 newtons per second in square centimeter for 60 days. So this is a huge efficiency and worldwide leading with this small amount of fuel element to produce such a high flux. So the outline of my talk is, I will start to give you arguments why neutrons are unique and very suitable for research on engineering applications. I have a few examples. I will talk about pipeline clocking, why I have the method PGAA and neutron radiography to solve the issue. Talk about residual stress in engineering devices with neutron diffraction, the irradiation of electronic components with fast neutron irradiation, needle clocking in medicine, neutron radiography, alloy development, neutron diffraction, small angle neutron scattering, electrolyte filling in batteries, neutron radiography. And you see on all these examples that there are many methods you can use really for engineering. And at the end, I will give a summary. So let's start with why neutrons are unique and very suitable for research on engineering materials. So the first huge advantage is that we have this very high penetration depth. of various probes. You see, you have electrons, X-rays, thermal neutrons, and cold neutrons. They can go up to centimeter, and this is a very good property which allows us to get really information from the inner part of the samples. So now, why neutrons for engineering materials? So first of all, we have this easy localization of light atoms, lithium, hydrogen, oxygen, nitrogen, besides heavy elements. This is very important because in X-rays, you have very often an overload of the heavy elements and you cannot detect the light ones. We have a separation of quasi-isoelectrical elements like nickel, manganese, and cobalt, which is very important in battery research because these are typical electrodes from these neighbor elements. And we have a large beam cross-section of a few squared centimeter for real bulk studies of complete components. This is important for workpieces, battery cells, and so on. There's easy handling of sample environment. So you have a testing machine for tensile compression, heating. The potentiostat can be applied while cryostat, furnaces, magnets, and so on. The deep penetration I've already mentioned. And what is also mentioned very often here at the workshop is this complementarity of neutrons with X-rays. So both together gives a good information, not a single one. And what is a huge advantage is that the energy transfer of neutrons for many experiments is a millievolt range. So this avoids damages in samples. Now the first example, pipeline clocking. So what was the situation? There was a company coming to us and said, there are problems with hydride plugging inside submarine pipelines. How can you help us in some way? So what happens? In a pipeline, you have air, a solution, then there are interfacial tension here on the walls of the pipe, and they start to get hydride particles, and then step by step, these pipelines are really clogged. So the question was now how to detect non-destructively these hydrides in a submarine pipeline, and on the other side, how to repair the pipeline. So what we have performed are 3 experiments as a kind of proof of concept with neutrons. So we measured the transmission to the inside of the pipe and try to get signals out of the pipe. Is it really possible to measure the inside of the pipe? Then we used another instrument to measure the hydrogen and carbon content of our prepared sample to qualify the material in the pipe. Is it really possible to detect what is inside the pipe? And the next step was then to measure with higher accuracy the hydrogen-carbon ratio on a modified setup to be really precise which kind of hydride is in the pipe. So here's the first experiment on radiography. So neutrons are coming in. Here is the original half pipe, 60 kilogram with all the shieldings. And here we have our sample. And the first positive answer is yes, we can detect this sample, can get out signals of the sample, so we can really study the inside. And on the other instrument, we have measured hydrogen and carbon ratio. Then we made another measurement to be more precise on the hydrogen and carbon peak. We modified this with thermal neutrons on a different instrument, but with materials, we have the same behavior like here on the original fast neutron beam line. And then with this, we are able really to detect the hydride. So the solution is there will be a movable neutron generator, which can go along the pipe to measure the hydrogen-carbon ratio signal and to identify the plug. And the located pipeline segment will be afterwards heated to destroy the hydride plug, and then we can repair the pipe in such sense that it works in the normal way. So that was a very interesting story where a large-scale facility and industry make a solution for a big problem. You can imagine a block of such a pipeline has tremendous costs for the companies. Okay, next example, residual stress in engineering devices, neutron diffraction. So very often when these tracks are prepared for trains, for example, you have such a roller straightening device to make in the last process reduction of residual stress. And you have also to check this, how precise or how's the residual stress in your track. So you have to do a stress measurement to be sure that this track will have a long lifetime and has no danger to get cracking or other issues. So this track was positioned on the diffractometer, and we want to compare this with FEM and validate also with a destructive method to see how precise we can determine with neutrons the strain and stress. So here we have put it in position, and then you see here all the methods together that, for example,
good for my plants at the back.
Mr. Lloyd, can you mute your microphone, please?
You're going anyway.
Mr. Lloyd, can you mute your microphone, please? Thanks. So then we have the neutron diffraction measurement, and you see here that together with the contour method and the straightening model, they are in very good agreement. So neutron diffraction allows really on these materials which cannot be penetrated with X-rays to get strain and stress, and then you can really make a prediction about the lifetime on this track component. What is also very modern is additive manufacturing. So how can we reliable measure residual stress in really complex structures made through additive manufacturing? So if you have, for example, here, so-called nickel-based superalloy, you need high penetration of neutrons really to get non-destructive measurements and to determine strain and stress. So with X-rays, there's no possibility due to the really heavy elements you have inside. With neutrons, you are able to make in 3D a full stress tensor. This means you have different direction. You put your sample, often with the help of a robot, to be more precise in different orientations, and then you measure the strain and stress. And here you have the direction, and then you can see that the values are in some range, which is useful because you can imagine here with such a complex component, you can save a lot of material on one side, and if you have the strength in the material, then it's very efficient to use additive manufacturing, because to produce such a component is very tricky. Good. There are also very often measurements on welded joints or thick walled pipes. Here, for example, we have one with 140 kilogram, and you see here in the middle part is the welding. And the question was, is it possible to calculate such welding and strain and stress and also to measure it? Because if you can do both and then you can improve your model, you can in future, of course, save a lot of money to use your very well, I would say, educated calculations. So here are many positions which were measured, and you see here in the horizontal and vertical line, and here's the welded part. And this is the result you see here on extent direction and axial direction, that the neutron measurements together with the calculations are in very good agreement. So that is really a method which you can use to improve your model when you do these measurements on selected pieces, and then to calculate this for similar materials. Now the irradiation of electronic components. Here it is useful to have fast neutron irradiation. So what was the idea? The idea was to irradiate many of these memory chips here, and then to see how stable they are or how many defects will be implemented with irradiation and what is the lifetime for these components, because they were used very often also for satellites and so on, where it is important to make in advanced tests to have an idea about the stability. So we have used different nutrients, thermal, cold, and fission nutrients, really to have different energy ranges. And here you see different setups with different materials in front for shielding and behind. And then the measurements were very interesting because we see that doing fast thermal or cold nutrients, the behavior on the different ships is quite various. You can see that a few of them react with only fast nutrients, other ones with thermal nutrients. And so you can really determine which ship is suitable for which energy range. And if you have problems, of course, you can think how to do the shielding to reduce your error per bit. So at the end, we had seen that especially the cold nutrients with lower energy, longer time to interact, also that they have the highest number of errors, around 140, comparison to 13 and 3 was the faster nutrients. Now, another example here is needle clocking in medicine, neutron radiography. So how to study the influence of external conditions on needle clocking. So clocking of needles in syringe used for auto injectors can lead to incomplete dose administration for patients. Yeah. So you have to see that the liquid moves into the needle during storage and solidifies there. And there are also parameters like storage temperature, storage time, and variation of pressure you have to consider. And here are the results. So here are different needles, and you see from the shadow, from the coloring, that there is a different amount of liquids inside. You see here the variation in temperature and also in storage. And here you see the storage temperature versus needle filling. And you see if you store longer, of course, you have more inside. And so there's also to consider that there's a diffusion of the water vapor. This makes an increased protein concentration. You have an exponential rise of viscosity, and then you have the clocking. And to avoid pressure gradients is the most efficient way to protect the needle for clocking. Yeah. Good. Now alloy development, neutron diffraction, small angle scale. So I would like first to give a short introduction on high temperature superalloys to get better understanding of the experiments. So superalloys are alloys based on group 8 elements. So nickel, cobalt, and iron are the basic. And then you have a few percentage of other alloying elements like chromium, molybdenum, tungsten, rhenium, tantalum, niobium, aluminum, and so on. So these alloys are very complicated. Why they are very complicated? They have to withstand very high mechanical strength, and they need a very high surface stability at high temperatures. So forces and temperature are the big players in this situation. And you can produce them in vacuum, cast in vacuum, and then subjected to several heat treatments. And there are many applications like hot working tools, fans, furnace mufflers, heat exchangers, turbochargers. And I'm focusing on gas turbines, engine jets, and gas transportation tubes. Yeah. Good. So that is, for example, in a gas turbine. Here, the inside with microscopy, you have these precipitates in a matrix, and these precipitates strengthen your alloy. And now the question is how to optimize the alloy. It means to control the size distribution and the morphology of these precipitates. And the other question is to follow the growth of precipitates under external parameters as temperature or tension, compression, which is typical for turbine in service. And here you can use very nice the Newton methods. You can adjust the lattice misfit of precipitates and matrix when you do different measurements, change different compositions. You can tweak the solution annealing, you can improve the heat treatment conditions, and you try various and compare the results. You can strengthen the grain boundaries, you can prove phase stability or transformation, and you can characterize this precipitate in the dissolution. This means at very high temperatures. And these are experiments under high temperature and forces. So here's an overview. When you increase the temperature, how neutron diffraction characterize on atomic level the different phases up to dissolution. The small angle neutron scattering, which is characterizing the precipitates in size and volume. You can really see how they grow, how they dissolve. You can use neutron imaging really to study a full turbine plate with cavities, air channels, cracks, corrosion on the surface. And you can use PGAA, which is prompt gamma activation analysis, to study trace elements, because it's important to know if there's some boron for grain boundary strengthening or hydrogen, which can be a source of embrittlement. Important is, as very often with neutrons, we have here in yellow these four methods I described. When you put your sample in your device, do this variation with forces, with temperature and so on, it is very useful to have complementary methods. So X-ray diffraction, SEM microscopy is very helpful because this allows you to get direct information in real space before you do any other experiments, and then you can optimize your neutron experiment. So there's also now in the last years the idea to go beyond nickel-based superalloys. Why? The nickel-based superalloys are limited in temperature. They can go up to 1100 degrees Celsius due to the melting range of nickel. And so there is the idea how to improve this. So one candidate is cobalt rhenium. Due to rhenium, there's an extremely high melting point, and this will allow a higher surface temperature, and higher surface temperature means less CO2 production and more efficient working in the engine. Good. Now I will show you one development with industry, how you can do such things. So first we identify with neutron diffraction different phases, and we observe with microscopy the strengthening carbides, which are here tantalum carbide. So then in the next step, we were identifying all the phases and were then doing high temperature measurements. On the right, you see that under certain conditions, there's a phase transformation from HCP to FCC. And we have also seen that the chromium carbides dissolve, so they are not stable, but the tantalum carbides are stable up to very high temperatures. So we can really use these precipitates. So now I want to show you what happens if we heat up to very high temperatures and then cool down the samples. So you see here we go to lower temperatures. So there's now a single phase, only the matrix, everything is dissolved. And then you can really see how these precipitates grow. And you see also how the mean particle size is changing. You can really control this size distribution and of course the volume fraction. And this of course is done with small angle neutron scattering, where you are sensitive on these particles. And you see on the right on the plot here how suddenly precipitation starts. Another example here is we heat up the sample to a certain temperature and then we hold at this temperature. So we can influence more or less you see here the increase in intensity. We can influence the size, and especially you see here that then the black curve comes to saturation, that then you have more or less stable precipitation. And of course with holding you can also influence very nice the volume fraction. So here are the SENS experiments in a different plot. Here you see the typical SENS signal, which is changing when we go room temperature, hold at very high temperature, and go down. And you can then calculate the size distribution, which is shown here. You see at 1200 degrees Celsius, we have a stable size distribution, which is good, because if the precipitates are too large, you will get problems with strengthening, because then samples can get brittle. When you go to higher temperatures, 1260, you see different behavior. At the beginning, there's a larger intensity increase, and then you see such a pattern. It looks like that they dissolve, which is not the case. They go out of the range of small angle neutron scattering. That means they are above 150, 200 nanometers, and therefore they grow too fast. That means this temperature 1260 is too high, but already 1200 degrees Celsius is a very good temperature to be stable. So to get more information, it is important to use testing machines for high temperature studies under loading, under compression, or torsion. This means phase transformation, strain stress, creep resistant fatigue studies. So you can, for example, study when you do creep exposure, the so-called drafting, where you get lamellar morphology. And for this, we have started with a loading rig of 50 kilonewton up to 1000 degrees Celsius. And recently we have improved this machine to 100 kilonewton and heating up to 1200 degrees Celsius. A very complicated machine, which allows us a lot of good and very interesting experiments using also inert gas to change the atmosphere and so on. And we can really measure the sample here in these very high temperatures. So now I would like to give examples with neutron radiography. Very simple, and this was also very often mentioned. There's also to consider that neutrons penetrate deeper in metals and provide a much better contrast in X-rays. From Burkhard-Schillinger, I have this example here to kind of introduction. To see here with X-rays, you have no contrast, but here with the neutrons, you see a lot of more details. I will now come to an example with a car company corporation. So car doors are glued today, and they need special rules, 100% gluing in this region and a very good sealing. All the things are necessary for the car companies. And we made now here a validation of a neutron radiography where we make defects before we glue. So here are gluing defects, which are in bright color. And then we made the gluing, and later on we have also rechecked that the gluing is correct. You see it here. And on top you can see when the sample is glued that you can really see the defects. And also here, a short comparison between X-ray radiography and neutron radiography. Here with X-rays in this region, you see not really good informations, but here all these bright issues here are from defects, and here neutrons are the only method to get really this detailed information. Good. About new battery research, a lot of things were said. I only want to show here in my group, we have these 9 methods. So they are really huge possibilities to characterize batteries on different time and length scales. I only want to focus on one example. And this example is to study the electrolyte filling in a battery. So we really want to see how this filling is running, because this is very important for industry. The industry likes to get 2 informations. How can I fill my cell as fast as possible? And the second information, is the cell really completely filled? So for this, we made a special setup with here kind of pouch cells. We had in advance tested different dosing, sealing, and different procedures, how to optimize this process. And here you see how these neutron radiography supports us very well in doing this. So here the pouch cell is fixed in the beam, and then we start then to fill the electrolyte liquid. And then you see it is not like filling a glass of water. No, they are bending, and from sidewards you get these filling, this wedding on these different layers, which I have shown in the schematic drawing. And very often it happens that you cannot really fill the pouch cell because there can be also other issues. For example, if you fill too fast, you see that there is also drops outside the pouch cell. You can imagine there can be gassing in the cell, there can be air bubbles. So you have to do this in a very good way. And therefore you have also to think about the geometry of your cell. And here you see a few tries how we optimize this to get faster this filling. And step by step, we were improving. And you will see in the next two sequences how we were coming step by step closer to a good solution. And you see here, for example, this one has a lot of gas trapping inside, and this makes it very complicated to finalize such a cell with a very good filling. So the next one, and then the final one. Here you see there's a lot of electrolyte also on top. So this can also happen that you have you stop your filling because there's a poorly wedding, and then you get not all the electrolyte inside, and therefore you have to also consider this very carefully. Good, and here this is the example where you see that we finalize in a very good way, and that is very important for industry, such issues. Good, here to see how all this behavior is, that from outside, from all sides, you have this process here for hard cell, which is also important, not only for pouch cell, it is working. And if you look more carefully also, how is from left and right, and how is the influence of vacuum or under air conditions, you can then make very nicely predictions, calculations with models to see these examples. And then at the end, what is important is that with vacuum and this special history in optimization, you can reduce the filling time by 50%. You can imagine if you produce thousands of cells, filling time reduction of 50% has a huge impact. Good. Now, my last example is a Zebra Power battery invented in South Africa. This battery works with electrode. One is sodium liquid, and that's the reaction of sodium chloride with iron, makes this iron chloride and sodium. It works at 300 degrees Celsius. It's very often used for trains for this application. And here, after studying the reaction front, we have also done tomography to see all the details here. And what was for us, of course, main important is to study the sodium level. And this was done here. So first we recognized left and right is different. So it's not like, again, filling a glass of water. There are differences. And when we were doing the reconstruction in 3D, then we really nicely see how the liquid sodium is in the battery. And you see here from the left part on the right image that the sodium has really different issues. So there's inhomogeneity, and it is good to know all this information also for optimizing these cells. Another topic in general, of course, I know also at Safari very important is the irradiation. So silicon doping We have a purely commercial production facility at the FRM2. Here's a silicon monocrystal for the semiconductor industry. And you use the nutrient transmutation. That means with nutrients, you irradiate your silicon sample, then you produce a phosphor. And with this doping, you can improve the quality of such a semiconductor material. And when you do this so-called neutron activation analysis, NAA, you can really measure on the level of concentration 10 to the minus of 15, a lot of different elements, impurities, and with these limitations which are set by companies, you can really show them how good are these samples. And then, of course, if you have less impurities, you have much better conductivity. And this is important for this commercial issue. So I would like to sum up. Newton's allowed to study in situ changes of engineering materials under the influence of external parameters as high temperatures and so on. And we really get bulk information of materials. That is very important with neutrons. If you have a synchrotron on X-ray, you have a very small beam cross-section, and here you have your real bulk information. The second point is neutrons allowed to study in situ operando the behavior of processes. So on different length scales, including phase transformation, morphology changes, and so on. So the observation of changes of the microstructure is under realistic working conditions and often non-destructively. The third point is neutrons allowed to study fundamental research questions in the field of engineering on various length scales from sub-nanometer to many centimeters. And we have real questions from industry which can be answered. Now I would give two further comments. One, what we do is we have a so-called platform for exchange of scientists and engineers. So each second year we have an event with industry where we have always different topics, which is organized from a committee called non-destructive testing of materials and components. And from the images you see, we have a lot of varieties on topics we study and exchange with industry. How to get beam time at our facility, I think it's also important for Safari, how they do, how we do. So we have standard proposals a few times per year with external reviewers. 30 to 70% of proposals are accepted, and you get the beam time in the next half year. We have also rapid access for feasibility study or to finish an open question. It's 12 hours without complicated sample environment. Results have to be published in scientific journals, and beam time is free of cost. Commercial beam time is also possible. So short waiting time with short proposal draft. You know, industry has not the patience like scientists. A short report of the experiment will be provided. There's no obligation for publication, and the cost per day are around 7,000 euro. I would like to thank you for your attention, and I open for questions. Thank you very much.
Thank you, Dr. Gillis. You are just emphasizing again 7,000 euros per day. Wow. This is very expensive. The floor is open for questions. Yes, Dion.
Thank you, Dr. Eels. Just have a quick question about the strain scanning you did on the the additive manufacturing sample. How did you account for partial gauge?
Yeah, very often we use for the quartz volume, minimum is 2.2 millimeters. And we can also increase this to around 8 by 8 millimeters. Yeah, that is how we do this in general.
Okay, thank you.
All right, thanks. Next. While he's going to the next speaker, I just want to find out regarding the battery that we're talking about that can operate at 300 degrees Celsius. What kind of an electrolyte are you using there that can withstand such a temperature?
To be honest, the electrolyte was not really provided by the company because it was a kind of secret. So what was our focus was, of course, to see how the sodium filling and the behavior is during operation. Yeah, I've only shown a short image because due to the time, but you can see this also in operando. And then you have, of course, many possibilities to improve these things. And this was really a special electrolyte, which was provided from the company.
All right, okay, thanks. Next.
For the alloy development experiments, what is the time interval for measurements? You know, what is the fastest measurement time that you typically use?
Yeah. So depending on the method, so when we do the diffraction, I would say each temperature we can measure, because this is with a single detector shot. So we do not step with the detector. We keep the detector on a fixed position, and then we can measure on each position between 5 and 10 minutes with a very good statistic. This is for diffraction. In SANS, we can do it much faster because there's also a fixed position where we focus on a special size, and then we can measure each 10 or 20 seconds, can sum up the patterns, and then we can optimize if it is better for statistics to put, let's say, 5 patterns together or to check really each single pattern.
Good morning, Ralph. It's Chitesh here. If you can go to slide 13, please, on the rail line. I noticed there was huge error bars at the top part of the rail. Maybe you can explain why these decreased as you went down.
Yeah, of course, very often the accuracy depends also on the thickness of the material. You see on top that when we here start in this way, we have to cross a lot of material here in this part. Here, of course, things are thinner, and here when we check more or less this part. So that is one issue. And of course, when you have such large pieces, it is not always so easy or so to put them really very accurate in the position that you keep the coach volume, let's say, exactly as optimized, because you like to do this with the defined changing in the movement of your sample. And then very often you have also at the edges to consider that there maybe your measurements are not optimized due to the movement of the whole sample. And that can be one reason on this issue. Yeah, you see also that foot and head with a thicker material have this larger error bar.
Any more questions? Andrew? Oh, can you just check the question in the chat, Ralph?
Yeah, 1 second. Oh, that is a question to an expert we had yesterday on imaging. So I think this is a question for Burkhard Schillinger, who will talk later on. This I'm not sure if this is really possible. Yeah.
Okay, the question is actually,
yeah.
Sorry about that. The question is actually on the shape memory alloy.
Yeah, I see that the shape memory alloys, is it possible to carry out spin resolved imaging? Yeah, and I would say that maybe an imaging expert working really only on this method can answer this question much better than me.
Okay. Any other questions? Just on the interest with regards to optimization of the super alloys. It sounds like it's a very complicated process to go through.
Yeah.
Do you get guided by some kind of a model before you can actually optimize this, the super alloys?
In fact, it is a little bit different. it is the companies, they have samples which are, let's say, nickel-based superalloys, which are more or less accepted from everybody due to the huge application they have. And then they try to slightly modify. And when they see, oh, this sample number 5 has a huge improvement, then they come to us and want to understand why this sample is better, or why some other sample has cracking, has problems. And then we figure out what is the reason to this. Or what we do actively is that we change, for example, heat treatment, because we see, for example, that there's something very interesting or some very fast kinetic. Then we try to modify this. So it is a game between industry and us to come together with one side, our improvement of the method, and on the other side, the changes in application, which have to be done due to cost or to be faster in production and all the things. And this all together makes the input on this really complicated alloys. You have to imagine these alloys are working at more than 1100 degrees Celsius. They have very strong forces, and if they are used for airplanes, they have to do 40,000 working hours without any problem. So the challenge is really huge.
Wow. I think that's why the price of 7,000 euros comes in.
Oh, to be honest,
Mr.
it is the more or less cheapest price in Europe. It is for a full day with support of users, as instrument scientists, with a report and all the things. Yeah, and to be honest, it will not cover our expenses for this experiment. When you take reactor cost and everything which is included, for sure not.
All right. Okay. Tsepo?
Yeah, thank you for the interesting presentation. Just on the stress profile of the weld, I don't remember what page it was. There was a little bit of a dimp in that profile. So I was just wondering if you can comment on that.
Can you, what have you in mind, especially on these patterns here?
Yes, yes.
So the idea was that an institute is doing this simulation, and very often when they made tests, they get problems that these simulations are not really fitting very well. And therefore we made this very precise study to take all these small quartz volumes here, step by step, in horizontal, and of course we can compare in vertical axis these strain values to get really a precise idea. Is this weld homogeneous, or are there special directions or special positions where we have a lot of strain, which can also lead to a embrittlement in the weld itself? So this on the material, because this tube was very important for application, and on the other side, to optimize this calculation that in future people can more rely on these calculations, we have performed this experiment. So there are two goals which we have tested, and you see that we can describe in a good way the calculations, which can be of course improved better, because you see that there are a few deviations on one side, and on the other side we can really see what are the maximum strain for such a huge component to be really safe when you check all the points on the welding.
Wow. All right, thanks, Dr. Gillis. The talk was quite interesting. There is one more hand, one last hand for you.
Morning, Ralph. Andrew speaking. You have different modalities for exploratory type of research, and if there's a collaborative involvement of the different institutes and yourselves, you also publish the work, of course, and then I assume that offsets some of the costs that you ask for the investigations.
Yeah. So there's a deal. If the company or the work cooperation with us do publication, we can do a reduction on 20% of the cost. Yeah. Of course, the challenge is, and this is what is not easy, is to get a company which pays on one side, and on the other side, the scientists get happy to publish. That is the secret how to do this. Yeah.
All
Very
right.
much.
Thanks very much. It looks like this discussion needs to be continued, and we've got a session in the afternoon whereby we'll discuss these issues. I'd like us to thank the speakers in this session. Thank you very much. Now we're gonna break for tea, and then we're gonna come back. I hope we are rejuvenated because we have realized the neutrons can do anything from 1 Kelvin all the way up till 1,500 Kelvin. So there is no one who doesn't fit in this band. Thank you very much.
The chest about.
Morning, gents. Dr. Walter, are you there?
Why? Yeah, but music I see is better.
It's not even, it's even not admitted.
How? Again.
Morning, gents. Morning, Dr. Walter.
Hello.
You are unmuted.
Sorry, you're very.
I just want to make sure we can hear you from our side. I can see you have got access to the screen. I can see you, but I cannot hear you.
Can you hear me now? Or
I can see you are talking. Try to check from your side if the volume is okay.
I can hear you, Jens, very well.
okay.
It looks like Ralph is. I can also not hear you. I think maybe it's from our side. Let's see if we can sort it out.
Okay.
John, can you try again?
Yes, I can say
Hello?
something. 1, 2, 3, 4. 5.
You are talking alone. I can just see your lips are talking, but I cannot
Okay.
hear what.
I hear him very well.
I hear him very well too.
Let's try to sort it out from our side again.
Okay, no problem.
It's probably from your side, guys. No, there is nothing still. They are not. They are not muted. Again? Can you hear anything from your side? Can you hear anything from your side? Okay.
I don't know. I can hear you clearly.
Yes. Can you say something again, Jens?
Yes, I can hear you clearly. 1, 2, 3, 4, 5, 6.
Yes. Now we can hear you. We just need to adjust our sound perfectly so that so that we can start.
So I can share my screen now, or what do you think?
Yeah, we can hear you, but we are just trying to sort out the fading. I think we are ready to go. You can just beam your screen. Let's see if you. Please share your screen and let us know if you've got permission. Yes, looks like it's coming. There you are. We're happy.
Okay.
All right, thanks. We'll introduce you just now.
Yeah, can you see my mouse? Can I work with the mouse? Can you see it? Just to show.
Now it looks like everything is fine from our side. We're just waiting for people to join in the room.
Okay.
Thank you.
Maybe yes, you could change the mouse pointer to a different option because we see the arrow, but it will be perhaps.
Oh, I don't know how to do this. Is there any option in Zoom or?
So you have to right click on your mouse button.
Oh. Sure. I have to.
I did. Colleagues, I think it's time. I think we can start. Colleagues, welcome back to our second session. And I think this is the last session where we have talks. And after the session, we have lunch. And please, after lunch, can we come back so that we can continue with our discussion session? So without wasting any time, I would like to introduce the first speaker for this session, which is Dr. Jens Walter. And Dr. Walter is a structural geologist who deals with quantitative microstructure analysis, the mechanisms and the process of rock deformation and recrystallization. And in recent years, he has been in charge of the realization of the sample environment for deformation and recrystallization experiments, quantitatively determine deformation or recrystallization mechanisms in a time-resolved manner. Dr. Walter, we are ready for you. Please share your screen so that we can start.
Yes, thank you very much for your kind introduction. Yes, and I want to talk in general, more in general, about neutrons and geoscience and the innovative research in our field that is possible by neutrons and the scopes for understanding Earth systems and the materials. So why are neutrons advantages for our geoscientific research? The first and to my opinion most important reason is that neutrons can penetrate large sample volumes.
Sorry, Dr. Walter.
Yes.
A little bit clearer. You sound like you are far away from the speaker.
I have it directly in front of my mouth. What can we do? Can we do it a bit?
Yeah, we're still struggling to hear you.
Okay. Do other people hear me clearly, or is it? Can I do something?
Just continue. I think we'll try to manage. Thanks.
Okay. Shall I speak a bit louder?
Better?
Much better.
We can hear
Okay.
you. Please continue.
Yeah, okay. So I want to start to just discuss why are neutrons advantages for our research in geoscience. And to my opinion, the most important reason is that neutrons can penetrate large sample volumes, as we often have coarse-grained samples, and we can only reach sufficient grain statistics with neutrons. If you think, for example, of salt domes, when we try to reconstruct processes, deformation and formation processes, there we often have very coarse-grained material. And the neutrons, in that sense, allow us to do research over scales, as we have to reconstruct geological processes from atom scale to centimeter scale, and by to go even larger than to outcrop scale in nature. So that's neutrons are a good link there. Then the second point I want to make, of course, is that we have the opportunity to precisely determine crystal structures or magnetic structures, phase transitions, as the neutrons scatter at the core, and not, for example, as X-rays where the scattering occurs in the electron shell. Then thermal vibrations are also accessible, quantifiable by neutrons, so by the determination of the scattering factors with diffraction angle, which then gives us the anisotropic temperature factors. Nevertheless, I want to state here, because I have the discussions very often with geoscience scientists, that neutrons are not the thing to do, but they are always complementary, and they will bring a lot of advantage to research, also with other methods where they are limited. For example, as I said, in grain statistics, or if you want to measure between local and global sample scales. Yes, and precision is also the one complementary factor of neutrons. Okay, so now I want to state the most important methods we are using in geoscience, at least to my knowledge. So this, of course, diffraction, where we determine crystal structures, thermodynamic properties, phase stabilities up to high pressures and high temperatures. We do texture analysis, so that's crystallographic or lattice preferred orientation, physical mechanical properties of samples. We measure stress, and what I studied here with colleagues also in the geobiology, to study geomineralization processes. Ralph, you're here also. Archaeometry is a field which also is adjacent to geoscience, and of course the small angle scattering, which is, I think, not so very common in geoscience. The next field is radiography, where we also have, for the last 10 years, or for over 10 years, the back edge tomography was also developed, where we can characterize melts, gain information about viscosity and rheology of melts, and also, of course, for microstructures, crack formation process, porosities, which goes into geoenergy and also all these fields. So there's a lot of knowledge or of gain we can produce. And the third field is the neutron or gamma activation, where we can measure concentrations of elements in materials. For example, also impact research, where we can define meteorites or which impacted by iridium or platinum group elements. Also, a project I had once was the provenance of critical raw materials, and of course, again, archaeometry, which is a field between archaeology and geoscience. So I want to state some examples from these fields, and this is quite a famous, was also published in Nature by, he's also my colleague, Werner Kuhs, who's quite famous or known in neutron community. And they had studied the formation and the thermodynamic properties of ice-16, which is a clathrate, and measured the possibility to store elements inside this clathrate. And you can see here what they found is that in the dependency of the temperature, we have a large variety of lattice constants within this clathrate. And to understand this is of great interest for technical storage of elements, but also for the stability of methane gas hydrates in continental shales. Or when you think of oil and gas transport in pipelines where plugs form, which are also clathrates, and in general interactions between water and gas molecules. This is another example. What can be done quite well is kyanite. We had studied the thermoelastic behavior and the thermodynamic properties from kyanite up to 1200 degrees Celsius, sorry. Yeah, you can see here the unit strain coefficient. And yes, this can be done very well with neutrons, as I said, because we can very precisely gain information about the structures of the crystals. Yeah, this is another example of magnetic structures in geoscience. There are, of course, many more in other fields of science where there's also a technical application. And here you just can see the difference between hematite and escolite, where the spins are parallel, but here in escolite they are varying in direction in the layers. So this is by Rudi Wenck. I got this work. So and yeah, for example, here they found out that hematite p-pole alignment varies with temperature and pressure. So this is research in that field. Yeah, and of course, speaking about diffraction, texture diffraction is also very important. Also, as you heard in the introduction, this is my field also of work. And yeah, when we talk about texture diffraction in geoscience, because of historical reasons, we have to quickly define the nomenclature. So texture is then here in this sense the crystallographic or lattice preferred orientation, and not what I've shown here in the SIN section, what we call the microstructure. So for historical reasons, this was defined in earlier times in the geoscience as the texture, and therefore we have some mix up there up to now. So that's why I define this texture, and then the microstructure is of course then the description of grain size, grain shape, and so forth. And yes, just to show you a simple sketch what I mean by CPO. This is so a random. The crystals are randomly orientated here in this material, polycrystalline material, and therefore we have sort of no or a weak texture. And here, opposed to the left side, we have preferred orientation of the crystals, and there we have a high texture intensity. That's in the base of what I'm talking about now. And yeah, there are two ways of generate texture formation in nature. On the left here, I like this image very much. That's from material science, where you input a material with a certain fabric, and then you roll. The material is rolled, and plastic deformation processes are in between, are happening during rolling, and afterwards you have a material with a different fabric and of course a different texture. And this is what we can measure. What up to now we cannot really measure what happens in between, and that's why I started this project where I will talk about in just some minutes. Okay, and analog here in geoscience, this is an image, a photo I took in the Alps, where you have the undeformed host rock, and then here the high strain shear zone and the intermediate zone in between. And you can see that this has happened under high pressure and temperature. And we can only, that's our problem in geoscience, we can only measure the samples, of course, after they have been deformed, and we don't know what was the input of here in this case we can measure because we see the input, but often we don't know this because of multiple maybe deformation events and so forth. So that's an ongoing research field in geoscience. And the second mode where texture can form are by biomineralization. Oh, sorry. This is also this is an American lobster, and the shell, and here also the material is composed of chitin and calcite as the main components. And here the lobsters build the shell by according to the mechanical properties of these ingredients, and to keep the shell flexible. And here the crystals are aligned to have the most stable orientation in this sense, so that they can enforce here in the claw, have a most enforcement here between the claws. So that's done by nature. Another nice example I like is teeth. The hydroxyl apatite crystals are aligned always with a maximum compressibility in this direction. So because the most pressure is from when we chop. So that's why these crystals are aligned in this direction, and this is done by genetically controlled processes. The same is here with in mollusk shells, where you find calcite and aragonite oriented in a very strong texture intensity. Okay, another example is also the texture can form in the atmosphere. This is an image from Antarctica, where you have strong winds and the ice crystals align in the wind and therefore form a preferred orientation, and then the sunlight is scattered, as we know this from our texture measurements in the detector. And most of you will see this as have seen this in the past as a halo around the moon or the sun. And this is when the water molecules or the ice molecules have no preferred orientation, then you see a complete halo. And yeah, the next example here is of course ice. When glaciers flow, then ductile ice deformation processes occur inside the glacier, and yeah, we find ice textures are commonly found inside these glaciers. So these are the most common texture formation processes, and when we know that the texture is a result from deformation processes, it's of course clear to study textures to decipher the deformation processes. And this is a very famous paper by Michael Stück and colleagues, where he showed for quartz for different deformation temperatures, so from top to the bottom with increasing temperatures, you see that this is, for example, the C-axis that you, or C-plane, C-axis planes, yes, 0, 0, 1, that you have a change here in orientation, and then they could study by field studies how that and other in combination with other analysis that you have processes which are not temperature dependent, and you can see also that deformation processes with increasing temperature. Oh no, so sorry, these are the porphyroclasts. They have not changed, and the recrystallized grains have changed in texture, in also the kind of texture. So different glide systems were active because of the increasing temperature, and so this is how we can use the field as lab for gaining information about the deformation processes. And yeah, this is an example for quartz, and this is another example for calcite, not less famous, where you can see that you have a development here, also with increasing temperature and also yeah, strain. The different types of pole figures here correlated with different types of fabric, and they also measured the thermal dilatation of these rocks. This was a project where these calcite rocks were also used as facade plates, and they bent, and the question was why. And so thermal dilatation was one physical property to examine, and that's why they did this. And of course they found that, not of course, but they found that these thermal dilatations are strongly dependent also on texture intensity, which brings me to the point that we don't. It's not only that we reconstruct deformation processes, but we can also define several physical mechanical properties of the rocks by texture analysis. This is another example where we mixed calcite and muscovite in different ratios, and we compacted these in uniaxial load and measured the texture strength. Here are the corresponding pole figures on the left, where we can see the development of the texture strength also in as a function of the muscovite content. And then we measured the anisotropic magnetic susceptibility, low field and high field, and then you can see that how the dependency is here between yeah, the load, the texture, and anisotropic magnetic susceptibility, the ANS. So this is another example where physical and mechanical properties are correlated with the texture. And this is another a bit old already, but very, to my understanding, not finished work and interesting work. The physical properties of the Earth's mantle. So, and this was, of course, we cannot go there, we cannot drill there, and therefore, in this study, they simulated textures according to seismic velocity differences. Also try to simulate mantle convections, and so we can. There are two main gains from this. This is to explore the seismic behavior within the Earth mantle and explore mantle convection cells, and yeah, by the mechanical combination of mechanical properties of the mineral phases and yeah, seismic measurements we have in geoscience. Yes, and so if there's this strong connection between these fields, of course, the idea was then quite clear to try to examine the by nutrients the deformation processes while they are happening. And this is why we started with colleagues from the RWTH Aachen in Jülich, and yeah, this is the Institute for Inorganic Chemistry of the RWTH Aachen University, to design a neutron diffractometer in TOF, time of flight instrument, where we can place large sample environments inside, and in cooperation at the same time, I developed then together with my colleagues here the deformation apparatus, where we can perform deformation experiments in situ in the neutron beam. And the colleagues from Aachen and Jülich, they developed the Vortex diffractometer. Vortex is powder and texture diffractometer. It's designed as a high intensity time of flight instrument, as a ballistic beam compressor. And of course, as we have a constant source, we need a chopper system. And this detector is specific for, or was specific then for Vortex. Now we have a sister instrument, which is called DREAM at the ESS, which has a similar detector setup. And yeah, this holds space for large sample environments. And here in Garching, where this is the FRM2 research reactor, our instrument will be here in the Eastern Hall. And behind our instrument, there's a large high pressure multi-annual cell, where they can reach, in the end, 25 gigapascal and 3000 Kelvin. That's built from the geocentrum in Bayreuth. And they are also doing diffraction for materials under extreme conditions, extreme high pressure and temperature conditions. Okay, this is the deformation apparatus we have developed. You can rotate it around omega, the vertical axis, and the sample sits in here. It's confined in pressure, uniaxial deformation, and the experiments are designed such that we can even use very slow strain rates, and we can bring the experiment continuously inside and outside the beam, so that we can measure the texture and the according deformation processes time resolved. And we can place this apparatus inside the beam according to the selected strain rate, and have control over the texture forming mechanisms by monitoring the texture during deformation. And of course, we have also control over the grain size, and we can decipher for the first time now then multiple active deformation mechanisms, because we often have make the experience that deformation mechanisms change during deformations, strain hardening, and all these factors. And this we can study now in detail, and have an understanding how finite textures develop over time. Yeah, so this is what we are now currently are able to do. We have uniaxial mode, confining uniaxial mode, and you can also cut the sample in such a way. Then you can also make simple shear experiments. And at the moment, we are only focusing on rock salt and carbonates with a maximum differential stress of 630 megapascal. Maximal confining pressure is 50 megapascal. Yeah, our temperature, which we have not running at the moment, but we are working on, is to have something like 1200 Kelvin, and our strain rates are in this range. Okay, and then for the ice community, we have developed also cooling rigs and not the rigs, but to perform ice experiments also at this instrument with constant temperatures down to 77 Kelvin. And due to the other different sample dimensions, we have maximum differential stress of 280 megapascal, but of course the same strain rates. Yeah, and this is, I think, the new option that we really can measure the time resolved texture during deformation according to the strain rate. And we have developed this deformation apparatus not only to compress samples, but also to this tensile strain on the stress and strain on the samples. This was together with the LMU in Munich, the group of Professor Schmal, and the advantage here is to be able to measure tensional stress strain and the texture simultaneously. So we can measure Poisson ratio and E module in our detector at 90 degrees to theta, and measure the texture of the grains with the rest of the detector coverage. So we don't need to first measure the stress or strain and then afterwards measure the texture in a second round. That's so it's a bit more efficient in beam time. Yeah, and this is the second sample environment developed together with the sample environment group in Garching at the MLZ. This is a furnace where we use laser heating. The laser light is put by this mirror and optic system here into the furnace inside here, and is then heats up the sample from each side very homogeneously, and we are able to rotate this sample environment inside the detector and measure then stepwise the texture, and then we can do orientation stereologic 3D reconstruction of the texture data, and then gain a 3D understanding of the recrystallization processes inside the sample. And you can heat up to 1800 degrees Celsius and use different atmospheric gases, but of course ambient pressure. So this is in our terms, this is a static recrystallization annealing experiments. yeah, that's what we do. What is my work in Garching, and yeah, to continue with our examples in scattering or in diffraction. Of course, we can use also small angle scattering in geoscience to calculate pair distribution functions. This is an example also by Rudi Wenck, where they studied CO2 as glass and as crystalline quartz, and then can see how the distances between the atom pairs are. So that's, I don't know, I'm not aware that this is done very commonly, but it's of course also geoscientific topic. Yeah, and the next field is radiography, tomography. I've seen that Burkhard Schillinger is there too, so he is a much more expert, of course, and he will, can show you more interesting examples also. But here, this is what I think is quite interesting to our field. Again, to image like cores like this, to get a quantitative microstructure, to get also quantitative information about cracks, crack seal formations. And this is a very nice example to work over scales with combination of X-ray, synchrotron, neutron, all on different scales. So synchrotron can go down to nano cores or nano structures. But you can also combine this with optical microscopy, SENT and AFM analysis. And we have a lot of unsolved questions in our complex geological materials about crack formation processes. We can use this for reconstruction of paleostress fields, and for technical applications in georeservoirs, where we now, especially in these times, is try to exploit geothermal energy, or this is spelling. Fracking is also, for fracking you need to understand how the fabric, the rock, the mechanical properties of the rocks are. Yeah, and also for storage, sequestration and storage of CO2, or now also storage of hydrogen. This is a hot topic discussed now. And another very interesting topic is the reconstruction of magma and lava.
Dr. Walter?
Processes. Yes?
You have 5 more minutes, including questions.
5 more minutes. Okay.
Yes,
yeah, I will finish off. Yeah, so another just short interesting development also in Garching was Mirko Boyn, who combined tomography with Bragg edge, and thereby we can combine tomography with texture analysis, quantitative texture analysis, and get, for example, quantitative understanding about crack formation processes which are dependent on the crystallographic orientation. So this is another very interesting application. And yeah, last but not least, of course, what I mentioned was the neutron and gamma activation methods, which we can use for impact research, as I mentioned, characterize ores or mesoral sediments, provenance of critical raw materials, also in technical devices, and again, in a non-destructive way for archaeometry and investigation of valuable goods. Provenance authentication are here the keywords. And then I thank you for your attention.
Thank you very much, Dr. Walter, for your talk. Colleagues, any questions from your side? I can squeeze in one or two.
One quick question. How does neutron tomography compare to X-ray tomography, especially when you analyze, something like drill cores for, say, for geological purposes?
I didn't get the question very much. So what I got was how to combine these, or
how does X-ray tomography compare with neutron tomography, with maybe regards to drill cores?
Yeah, we have different. So with neutrons, you can access very large drill core or large volumes of the drill cores, but the resolution is not is of course a bit more is not so fine as in X-ray. X-ray has a finer resolution, but you cannot access as large sample volumes. Then you can go to synchrotron, where you also can access large sample volumes, but you have a very small beam, and therefore you need a lot of beam time. So in that sense, you always would need to see what are your geologic or your questions you want to solve. What is the necessary resolution, and then you select the method by that. Did that answer your question?
Sorry.
Yes.
Next question, colleagues? If not, I think we should move to the next speaker, since we are running 2 minutes behind.
Sorry for
and let's thank the speaker. Our second speaker for this session is Dr. Florence Porsche, who originally specialized in single crystal X-ray diffraction and completed her training in neutron powder diffraction at LLB. She was delegated to CNRS as part-time researcher and came in charge of the high resolution spectrometer and was responsible for building the high flux, long wavelength diffractometer, as well as the high resolution cold diffractometer. And during this period, she kept doing local contacting on the unpolarized single crystal diffractometer for studies in line with her own research. And over to you, Dr. Porsche. Thank you.
Thank you.
Okay.
So, oops. Sorry. Sorry. Yep. I'm supposed to share my screen now. Can you see my screen?
No. We can't see your screen.
Please share your screen.
Yes, I'm supposed to do it now.
Okay.
Okay. Okay, let's do it another way. Trying again.
We still cannot see your screen.
Yep.
We can see you. Yes, it's coming. Yes, we can see it now.
Okay, perfect.
Thank you.
I can't see my screen now. That's even worse. I can't see my own
screen.
See it. Yes, but I can't see it anyway anymore. Okay. And now?
We can see your screen. Can you see the screen
Yes,
as well?
it's, okay, it's better for now. So thank you, Mr. Chairman, for the kind introduction, and also thank you for the invitation to this meeting. So I'm going to talk about a molecule inserted in porous system, and I will try to illustrate how neutron scattering in conjugation with other characterization techniques can lead information about the interaction of the two subsystems, the matrix and the gas molecules, from the point of view of the matrix, but also from the point of view of the gas molecules. So it's we're going to present results which have been realized with other French collaborators over the last 10 years. So to be short, what are the porous materials I'm going to talk about? So according to EUPAC, the porous materials are classified in 3 families according to their size, their pore size distribution. The microporous are systems with lower size for the pore, less than 20 angstroms. They are in general crystalline materials, and representative of this family are the zeolites and the metallo-organic framework, or MOFs. So for this system, as they are crystalline, it's possible to have a model of a matrix at the atomic scale by diffraction. The second intermediate family is that of mesoporous, which have porosity between 20 and 500 angstrom. These materials are semi-crystalline in the sense by the walls are amorphous. In general, it's amorphous silica, but the pore structure is so regular that it gives rise to diffraction peaks. And for this material, the porosity is very well controlled, and it's possible to obtain a model of the framework at the scale using stronger scattering. And the last category, that of macroporous, exhibit the larger pore size, but the pores are less controlled, or not very well controlled, and I will not speak about that, this kind of system today. So why studying such systems? Of course, because they are of wide use among the industry. They are used for catalysis, ion exchange, or absorption, mainly. And for there are some most focused applications which are foreseen for immobilization or protection of sensible gas molecules, as for example for drug delivery. And as you can see on the left table, most of the application relies on zeolite, and to the extent on MOF and mesoporous material are really, really seldom used. There are many kinds of zeolite, MOF, and mesoporous, but among these kinds, only few of them are widely used by industry. And during this presentation, I will speak about the phosphazite, MFI zeolite, MIL53 MOF, and the MCM41 mesoporous. So all this process relies on the interaction between gas molecule and matrix. If we consider the Oehenberg-Cohen theorem, the energy of the ground state, or the ground state itself, is a function of the electron density of the host and the electron density of the gas molecules. We will consider now the situation where the two molecules, gas and the molecules and the matrix interact not strongly enough to give rise to chemical reaction, but it excludes hence catalysis. So if we exclude catalysis, we can go to sorption process, for example. And in order to understand the interaction, we will proceed differently for mesozeolite and MOF and for mesoporous. In the case of zeolite of MOF, we have an atomic scale model for diffraction, which allows to predict property of the gas molecule adsorbed, for example, by statistical dynamic calculation. And from these predicted properties, by comparison with measurements, it's possible to validate or not the interaction model. In the case of mesoporous, one usually goes the reverse way. First, measuring the property of the gas adsorbed in the mesoporous, and then try to model empirically the properties at the interface between the matrix and the host, the matrix being in bulk quite insensitive to adsorption. So looking at the atomic scale in the case of zeolite and MOF. So in short, presentation of zeolites and MOFs. Zeolites are the older family, they are inorganic materials. Framework is built from TO4 tetrahedra, bridged by oxygen atoms. And the 3D framework, which is based on this arrangement, gives rise to about 150 topologies, which is arrangements of channels and cavities and shape of channels of cavities, where the gas molecule can diffuse. If the framework is neutral, which is the case in pure silicate framework, the zeolite is hydrophobic. If there is a substitution of silicon atom by 3+ aluminum atom in the framework, then the framework becomes negatively charged, and there have to be some cations sparse in the cavities, which is the case of phosphate, sodium aluminoxylate phosphate, and in this case, the zeolite is hygrophilic. In the case of MOF, by analogy, the framework is built from super polyhedra, tetrahedra or octahedra around metallic centers. This tetrahedra is bridged by organic linkers, and there are hundreds of topologies. And in the case that all the polyhedra are tetrahedra, one has topologies which are totally similar to that of zeolite, except that the porous size are larger because of the size of the linkers. And as these linkers can be quite easily replaceable by a longer linker, there is a possibility to scale up the size of the porous system by changing the linker. In general, aryl or alkyl linker are used for the formation of MOFs, and MOFs have an hygrophobic character. However, if there are some open vertical site or hydroxyl group inside the framework, then the system acquires some hydrophilicity. So, how to model the interaction on this crystalline material? Ideally, one will do it by an initial calculation, calculating from the wave function the electron density of the total system or only the empty matrix. And from these quantities, predict thermodynamical absorbable like absorption curves or diffusion coefficient of a gas molecule inside the framework. This is not always possible. So another way, which is most common, is to obtain through diffraction the structure of the materials, and in the case of high-resolution X-ray diffraction, maybe extract the electron density of the system and experimental charges that can be transferred to Monte Carlo simulation. And this basic empty structure is put in contact with a reservoir or gas molecule whose position and distribution is obtained by optimization and allow to deduce all the thermodynamical observable like I said before. And this observable can be compared to experimental ones. So first example of application, the case of simple case, the case of empty hydrophobic silicate MFI. So what you can see on the left is a sketch showing the crystal structure of MFI compared to that of quartz and coesite, which are two other polymorphs of SiO2. So as you can see, the structure of MFI is much, much larger. And before going along with the presentation, one has to know that in the case of purely silicate MFI, there is a phase transition about room temperature that gives rise to quite a strong deformation of the framework from a circular opening of the channel to a ovoid opening of the channels. So this will affect, of course, the diffusion coefficient and the absorption curves. So in this case of MFI, no ab initio calculation are possible because the system is much too large. So one has to proceed another way. And for example, we were interested in trying to determine the electron density in the system through high resolution X-ray diffraction. Remembering that the structure factor from X-ray diffraction is a Fourier transform of the electron density of a crystal. So from the Bragg intensity measured from X-ray diffraction, it is possible to obtain the electron density of a total system after a decomposition of the atomic components. And this decomposition is performed by splitting the atomic electron density distribution into core, charge, and deformation terms. The procedure is the same as the one which is used to extract spin density from polarized neutron diffraction. And if we do so, normally we should be able to obtain charges, atomic charges, so-called kappa charges, PV kappa charges. So this is what we have done in MFI. So we have modeled electron density experimentally in MFI, did the same in the case of alpha quartz, and you can see that the total electron density is the same quality in both systems, the simple one and the complex one. It shows the expected value, bonding character of electron density between silicon and oxygen atom, lone pairs on oxygen atom, and so forth. And also, the electron density model is of the same quality as that obtained by periodic R3-Fock or R3-Fock DFT model on cohesite and alpha quartz. So it means that the electron density looks good. And so the PV kappa charges obtained for this system, experimental charges, should be also good. And one good point at this stage is that we obtain charges which are comparable to the electronegativity equalization method charges, which are widely used for Monte Carlo simulation. So how good are these charges? So this is an excerpt of literature about adsorption and diffusion of alkane in MFI purely silicated. So what you can see on the left is the experimental absorption curve in red for normal heptane in MFI, and the result of calculations using atomic charges which are not very far enough, a bit more stronger than the one obtained experimentally. And the simulation is performed using the open or the undistorted, the circular channel model for the MFI or a distorted model. And as you can see, the reproduction of the absorption curve is quite good, in particular using the undistorted channel model. For the diffusion coefficient of different alkanes from methane to octane inside the MFI, there is calculation also performed with rigid or flexible framework, the same as before. And one can see is a good agreement between this calculation and the experimental data point obtained by quasi-elastic neutron scattering by O'Malley and Jobbik. And this seems very good, but in fact, it's a bit deceptive because for the diffusion coefficient, values obtained by QNS can differ by 1 or 2 order of magnitude with the experimental one obtained by pulse field gradient NMR. So experimental data can be quite contrasted. And also, we know that such system, there can be few silanol groups, and these silanol groups in the silica walls can influence strongly the diffusion of alkane molecules. So one thing is better is what we can do structurally with such a system. So we were interested some years ago about stabilization of molecules of paranitroaniline in order to obtain good second harmonic generation materials. So paranitroaniline is quite a small molecule. And what we did is that we loaded in vapor phase methyl crystal with PNA. and measure the second harmonic generation signal in the material. And what you can see is what we hope or expected, that the second harmonic generation signal is larger when the polarization of the laser comes along the direction of a straight channel of the MFI. So it's what we expected. So we went them to neutron diffraction, where we perform experiment on the low resolution but high flux non-polarized diffractometer G41 at LB, on the empty matrix in blue and on the PNA loaded matrix in red. And from this experiment, it was possible to locate the PNA molecule in the framework and to see that these molecules are very well localized. There is no difficulty in finding them in the refinements. And not only that the position of the molecule is precisely at the position of the pockets of electrostatic potential calculated with experimental charges on the MFI. So it's also a good argument in favor of experimental charges. We also perform some quasi-elastic neutron scattering on this system that shows that there are no translational diffusion, which is in agreement with the good stability of the compound. For more than 10 years, properties are preserved. And also, there was some tilted or rotation of the RB group, phenol group of a molecule inside the cavity, which was also confirmed by the isotropic displacement parameter of atoms from diffraction. So that was simple system. Getting to know a more complex one, the hydrophilic fauxjazite zeolite FO. So in this case, we were interested in knowing what were the respective role of water molecules and cation distribution from each other, knowing that the water molecules are necessary to obtain cation exchange in such zeolites, but also the stabilization of water molecule depends on the distribution of cations. So as we say in France, it's a problem of chicken and egg. Knowing one is knowing the other one, or not knowing one is not knowing the other one. So in the case of fauxjazite, aluminosilicated fauxjazite, the structure is quite complex. There are plenty of cation sites, as you can see in green here. And for convenience, the sites are labeled by standard name. And on this simplified sketch of the zeolites, you can see that there are site 1 and site 3 and 2. And what has to remember that site 1 is this kind of hexagonal prism, is a position which is not accessible to water molecule, while site 3 are very accessible to water molecules. So, in order to understand this reversible influence on cation and water molecules and reversely, we perform experiment on the bicationic zeolite, nickel sodium Y zeolite, which is used as a catalyst. And for catalysis, it's necessary, of course, to have the gas molecule enter before for the cracking, for hydroisomization, and that the sample is activated, which is in fact dehydrated. And this activation step is critical for the quality of the catalysis. So what we performed was an experiment on starting hydrated Y zeolite, fully hydrated Y zeolite, where we progressively dissolve the water molecule by heating up the sample. And we use for that non-polarized neutron diffraction on a system loaded with normal water. The aim was to see if we can use the incoherent background from H1 hydrogen atom to quantify, at the same time as we see the evolution of the crystal structure, the amount of water in the system. And as you can see on the right sketch, the orange curve, which is the incoherence signal, is reproduce very well the signal obtained by thermogravimetry on the same kind of sample. So yes, from incoherent background scattering, one have valuable information about the hydration state of the zeolite. So G41 spectrometer used before was not a high resolution diffractometer, so it was difficult to start refinement from the data. So we went to another high resolution diffractometer at LLB. But of course, the measurements are much slower, so we did analysis only for 4 temperature. But from this data, we were able to see that there was quite a clear cation distribution, redistribution between for the various temperature. For example, for fully hydrated sample, the nickel atoms in greens sits in the so-called site 2, accessible to water molecule, and progressively upon heating, relocate inside the hexagonal prism. And this relocation comes along a very strong deformation of the framework around these atoms. So knowing this intermediate structural point, we came back to the low resolution data set and were able to refine the structure on the cation, the framework and the cation distribution, assuming some few constraints. And what can be seen on this sketch is that there are a very strong deformation of the framework angle changing by more than 20 degrees from the room temperature to the dehydrated state, for example, for oxygen O4. And this deformation is permanent, meaning that coming back to room temperature, the deformation of the framework is preserved. And this deformation also comes with a redistribution of the cations. In particular, the nickel cations goes definitively in the site 1, which is not accessible to gas molecules for catalysis. So this explains why activation process on nickel sodium phosphazite was under a kind of reduction when the sample is heated too much or too fast, and why there is also an amorphization of the sample during heating. So one bad point of this kind of this experiment, however, was that we were not able to locate all the water molecules. We were only able to locate 10% of them. So we would have liked to have a model for the remaining water molecules. So for that, we made a complementary study on a parent system, which is cobalt sodium phosphazite. And the idea was to transfer atomic charges obtained from high resolution diffraction, X-ray diffraction, to the ground canonical Monte Carlo simulation in order to provide this simulation starting structural model and charges for their force field. And from the Monte Carlo simulation, obtain this cation, a distribution of cation and also distribution of the water molecules. So this diffraction Monte Carlo interaction proved to be quite effective because the result about the cation distribution was in very good agreement, as you can see on the left sketch. And also it gives us information about the location or the non-location, in fact, of the 90% of water molecule missing in the model. So this also proves that for such kind of hydrated system, it's necessary to have a non-atomistic model for water molecule, which is a kind of model that can be obtained by maximum entropy, for example. So last crystalline system, the MOF archetype 1053 in its aluminum form, meaning that aluminum is at the center of the tetrahedron, of the octahedron. Sorry. So 1053 is an archetype system of MOFs, and it's also a very favorable system for neutrons because the linker is quite simple and can be deuterated quite easily. So it is a system which is well known to endure a strong change of phase transition between an open form and a closed form phase as a function of temperature with a very large hysteresis of about 200 degrees. So we started the measurement by neutron powder diffraction and synchrotron diffraction in order to characterize our sample, which is deuterated. And we checked that the hysteresis was present. You can see here the open to close temperature, which is about 150 K, and the close to open phase transition, which is at 350 K, for example. So the data we obtained was in line with those obtained by other methods, and we noticed that there were no degradation of the sample after cycling 5 times. So we also noticed at this time that the sample used for neutron diffraction was not closing fully. About 10% of open phase was still present at low temperature, and probably because there were some residual water inside. So we also went to high resolution for the diffraction on this system, the synchrotron and neutron. And we observe the usual transition between the open and closed phase. We are able to refine both phases by neutron and X-ray diffraction. And we also perform an MR simulation that proved that the force driving the transition was a spin flip movement of the R-wheel ring during which was getting the flip was getting more and more frequent, and was the driving force for the closure of the system. This was also in line with the structure we found for the open phase. What we found also is from synchrotron X-ray diffraction that there was most probably an additional third phase, which is probably a distorted narrow pore structure at low temperature, but it was sadly not possible to solve the structure because there were only few drag peaks. So this system is also interesting because there is another hysteresis between the open phase and the low phase at room temperature when water is introduced inside. So we perform also experiment on the dried and pseudo-dried and the hydrated sample, from which we were able, thanks to neutrons, to locate the hydroxy group responsible for water absorption in our system from the open phase, and also some water molecules in the totally hydrated sample. But the model was correct, was fair, but not totally satisfying because the refinements were highly unstable and the water coordination was quite strange. And one problem with this kind of sample is that it's difficult to know how much water is expected inside it. And it's a bit deceiving because we were expecting to have much better information from neutron diffraction, but we will have to look again at the data. So that's the end for atomic scale modeling of microprose. So let's go then to system that I'm much less used to because I'm crystallographer, the mesoporous MCM41. So the MCM41 are mesoporous material with an honeycomb pore structure. They are well known to have a very reproducible surface and very uniform pore distribution, and rather small adjustable channel size between 15 angstrom and 100 angstroms. And you can see on this sketch how accurate is the pore distribution for various pore size. It's really, really well controlled materials. And contrary to SBA15, there is no interpore connections. So there is a simple mesoscopic model for MCM41, which is that one, honeycomb structure of straight channels. So when the MCM41 is crystallized, or is synthesized, in fact. The wall pore are decorated with organic linkers. The system has to be calcined. And once calcined, the inner walls of the pore are hydrophilic with many silyl groups. And it is possible on this system to obtain hydrophilic and amphiphilic and hydrophobic system by grafting nonpolar organic group on the silyl group, and then to change the properties of absorption of the molecule. And you can see here the absorption curves on an hydrophilic material with a high absorption rate, on that on the hydrophobic material with much less water molecule getting inside and at much higher pressure. So the main techniques for characterizing the matrix, MCM matrix, are mainly small angle and TEM.
Can't hear you. Can you hear us?
Sorry? Okay. Main techniques for characterizing.
No, you can continue. We lost you.
You lost me? Oh, sorry. You hear me now? Do you hear me?
Yes, we can. Please continue.
Okay. So main techniques to characterize MCM41 are in the direct space or in the structural phase, the small angle scattering and the transmission electron microscopy, and and also nitrogen or water absorption to characterize for accessibility and hydrophobicity. So what you can see here is a typical nitrogen absorption curve on MCM, various type of MCM41 with different grafting molecule from the hydrophilic one to a very quite hydrophobic one with amount of water molecule absorbed is different. And the capillary condensation stage is the one where there is a layer of water molecules sitting on the walls, and it's a reference stage for N2 absorption. These data can be combined with small angle neutron scattering data to obtain this information about the pore size and the pore characteristics. So this has been done for various MCM41 matrix with different kind of structure at the wall pore. This is publication by Cristiana Bassini-Monesco and Nancy Litter, Fabrice Omnet, and Reichhoffel from LB. And combining these two information allows to have from the neutron scattering the size of the pore at the silica walls, and from the nitrogen absorption, the size of the accessible pore, meaning functionalized pore, and the difference between the two allow to define wall thickness. And this wall thickness give information about the length or the effective length of the molecule grafted, and then if these molecules are tilted or not, and what kind of fragment they can present to adsorb molecules. This also give information about the dimensionality of the pore after calcination or after grafting, which gives you information about how good the pore structure is, how regular the pore structure is. And this says that there is no degradation by the grafting performed on these materials. So from the point of, sorry, something that went wrong. So then from the solvent point of view, in the case of hygrophilic MCM41, the idea is to fill via the MCM41, which is hygrophilic, by vapor phase water or by impregnation. And the pore loading can be controlled by controlling the partial pressure on the absorption curve. And when one is before the capillary condensation, there is only one single layer of water molecule on the pore. and after capillary condensation, there are some water inside the pore, inside the wall, very inside the wall, not close to the wall. So characterization of such a system is often performed first also by DSC, and DSC gives information about the melting and crystallization temperature of water inside the pore. And it is well known that there is a kind of so-called melting temperature depletion, which is a variation of the temperature of melting as a reverse function of the size of the pore. The smaller the pore, the more difficult it is to obtain crystallized water inside. And in the case of hydrophobic MCM41, it appears that the limit size for the pore for nucleation of ice is about 20 to 25 angstroms. SENS also can bring information about the status of the water molecule adsorbed at the layer for small loading, for low loading. And what you can see here for, in fact, for intermediate loading, this kind of sketch, is that at close to the walls, the water molecule are in the so-called low density amorphous states of water. And when one goes to large pore system, larger than 2025 system, and one can go to neutron diffraction, and the neutron diffractions have confirmed that depending on the temperature and the pore size, one obtain crystallization of cubic and hexagonal ice form, and for intermediate stage, in fact, defective stacking fault cubic ice with faulted hexagonal planes, which is something which is quite common in the hydrophobic moth. For the hydrophobic moth, then that's a domain where no one has gone before, meaning that there is only very few information that can be found from literature on this kind of system. This can be understood because in the hydrophobic materials, water does not enter easily, and one has to push on it, and meaning that one has to use some gas cell if one want to do diffraction or scattering measurements, and in this case, neutron penetration is a great help. So for penetration pressure inside the hydrophobic materials is of course proportional to the reverse of the pore size. Here you can see a set of zeolites when you have to a very small pore size, and pressure, intrusion pressure needed is already hundreds of megapascal. For functionalized MCM zeolite, the pressure is even higher, and different dependency because, of course, of the hydrophobicity of the walls. So what can be seen from diffraction is that on this kind of system, there are a different behavior of water adsorbed as a function of the loading, which is either it's in capillary state, if ever you have full loading in the, or partial loading inside the pore. And this can be, when for very low loading, only amorphous water or amorphous ice is found close to the walls. And then for intermediate loading, there is cubic ice, they're not defective, or almost not defective. And for very, very high loading, the classical hexagonal ice is formed. And there are also various behavior as a function of hydrophobicity of the material. Of course, the temperature depletion, but also the crystal size of the ice form is changed. So this is starting of a story, but as a crystallographer, I'm not very fond of mesopause materials. And my next background would see to consider confined water in hydrophobic moths. So here is a sketch of moth 74, a small one here, which has a typical pore diameter of 14 angstroms. And this MOR74, of course, can host metallic ions inside its tetrahedra. And when people say metallic cations plus aryl ligand, then one say, okay, magnetic properties plus conjugation, meaning propagation of magnetization. And indeed, in the case of cobalt-nickel MOFs, there is a magnetization that can be changed as a function of the adsorbent. And there is also a phase diagram between antiferromagnetic and counted antiferromagnetic phases as a function of the composition. So one can expect is to be able to change the magnetic state of this system by changing the pressure or by changing the amount of water molecule inside the core. In the case of MOF74, it's a very interesting system because it shows a very strong scalability of the pore size from 14 to 9600, meaning that for some intermediate, there are some intermediate pore size when one should be able to see water crystallize inside a crystalline material, meaning a material where one can expect to have an atomic scale model. So that could be a very interesting playground for crystallographer. So I'm going to finish it because my time is elapsed, and thank you for your attention.
Thank you very much, Dr. Posha, for your interesting talk. Colleagues, we can squeeze in 1 or 2 questions. Any questions from the floor? Okay, if we have no questions, maybe we can thank the speaker once more time, then we move on to the last one. Okay, the last speaker of this session is Dr. Pukat Schillinger. He's not a stranger to Nexa Neutron Imaging Group. He's done a little work with our colleagues, and we are delighted that he's here today. He currently works.
So can you hear me now? Hello, good morning. Oh, can you hear me? I have activated my microphone, but it seems like you cannot hear me.
I can hear you.
Yeah, I can hear you too.
Okay, but Robert cannot hear me.
It takes a while that they can hear you. You have to wait.
Okay. Robert, I'm waiting for your sign that you can hear me.
Yes, we can see it now.
Yeah, but can you hear me?
Yes, we can hear you.
Okay, now it works. So I was waiting for that.
Okay.
Good, thank you. I will now let you relax a little bit with a lot of colored images. I will go into some very curious specific applications in paleontology after a few initial examples. I hope you will like that and relax a little bit after this really tough talks previously. Let's see. Only it's not working yet. Now, okay. I'll just go very quickly over this because you've heard already a day of talks. Of course, X-rays interact with electrons and the position in the periodic system. When neutrons deliver contrast to many light elements, and often you see contrast between neighboring elements or even isotopes. So for paleontology, it's useful that neutrons deliver contrast for bones and teeth in chalk rock, even in ferrous rock, especially in red beds, which is iron-containing rock, which you cannot easily otherwise look at. I just wonder why I do not see my own transparency given the talk. Okay. So, and especially neutrons still deliver contrast where fossilization has exchanged minerals, which I will show you in a few moments, making features indistinguishable for X-rays and synchrotron radiation visible. So very briefly, for a reminder here, this is the attenuation coefficient, neutrons versus X-rays. Of course, interesting is hydrogen gives a very high contrast, iron somewhere down here, below the X-ray curve. So we can penetrate a lot of things, especially rocks. I will not spend much time here. This is again in grayscales. So you can see a lot of contrast again on water, but we can easily penetrate lead. I'll skip over that. Only one slide about our facility. This is the Antares facility at FRM2. We built 2 measuring chambers. The funny shape is because we are in the corner of the building and we had to build this center wall here. And originally we planned to have really large objects in this area, and today everybody comes with centimeter-sized samples, so everything is performed here. I will skip over that. So the methods for cultural heritage that we use is standard neutron radiography, of course, computed tomography. You can also do breakage imaging, energy and wavelength scans. And I will not talk about neutron grating interferometry today. This is more for artifacts made from metal of interest. With some very quick examples, like a Roman statue that we can penetrate, where you can see some leftover of the casting core inside, maybe a little door, maybe the casting core was taken out here. This is a sealed Roman vase, which is very light and was presumed empty. And with neutrons, we can see there's powder inside. The first guess was plant seeds, probably is kind of a cosmetic powder. It still has not been opened, so we cannot tell details. It's another early example of our measurements. This is an excavation of a knife from the Iceman, Stone Age. And we could distinguish the flint blade and the birch pitch that was used to glue it to the handle and the wooden handle. Some organic materials in contrast with others, very well visible. It's another early example. This is an early medieval sword from the 7th century, where we could reconstruct the sword inside the scabbard. And inside the scabbard, we even found little pieces of wood that were put in there to keep the sword from scattering and clattering within the scabbard. Another Roman coin, which was totally corroded. And this is actually a cut, not a real surface extraction, where we could find the printing underneath of the corroded layer. Then we also had some textile archaeologies. This is just one fragment of textiles. It was even more important, but that stuff was stuck to the hilt of a knife, so next to steel, and we could of course still do tomography in spite of the steel, which would not have been possible with X-rays. So we could even distinguish the weaving technique on this. This fragment is about 4 or 5 millimeters big. Then there was an example from the Deutsches Museum here, where we looked at historical lenses. X-rays do not reveal that much. With neutrons, you can get a good image. And we also see that probably at least one of the lenses was made from boron glass, because it's very dark to neutrons. Here there was a whole series. We even had an exposition in the museum with the original lenses and the neutron images of these. Well, I can go into more detail in a moment about teeth. This is just a human mandible scanned by neutron CT, and I will explain you why neutrons were special in this case. Before we do that, let's talk about monochromatization. We can do a monochromatic beam either with the velocity selector, which is this kind of turbine here. We can imagine if this rotates fast and just one speed of neutrons would fit between the blades. The other possibility is using a double crystal monochromator. We can have even finer wavelength resolution, but of course then we also lose intensity. Okay, I've probably heard a lot about Bragg's law, where you get coherent reflection of neutrons on a crystal lattice, and that works up to half the wavelength equal the lattice distance. That's the maximum. And what turns out is you get this kind of Bragg edges in absorption if you scale over the wavelength. That means in attenuation increases, also scattering increases until you reach that parameter, the lattice parameter with half the wavelength, and then with the wavelength becomes longer, coherent scattering is not working anymore, and suddenly get a drop in attenuation here. And by measuring those breakages, it's possible to determine different kinds of steel, different alloys, which was, for example, done by Francesco Grazzi, one of our most avid users. He always brings weapons, medieval weapons like swords or axes or even armor. And there's many more pictures in the meantime. He even looked at, what's the name? Sorry, Damascene steel, where different steel kinds of iron were twisted and smithed together. Unfortunately, the movie is not working in the slides he showed me, but you can even see here, we measure at different wavelengths on the sword, and you can see different contrasts for different phases of the steel in here. So sorry, I cannot show this. This should have, yeah, this file is left. I don't want to look at this. I want to talk about teeth, like hominin and non-hominin primate dental fossils, fossil remains with neutron microtomography. That was an interesting thing because I was listening to a talk at the geology department where Clemens Zanolli was a guest and giving a talk. He worked at the Trieste, the synchrotron in Trieste for a time. He's originally from the University of Toulouse. And I told him that we had gotten some rocks from South Africa. And then he said, I have a PhD student who would like to examine those. And well, about this is the history. How to do that. The collaboration started, I know, probably you know this better than I do. You have the cradle of humankind in South Africa. There's a span of limestone caves. It spans half the African continent, and sometimes roofs collapses. A trap is formed for animals and humanoids alike. This is a wonderful display in your Ditsong Museum in Pretoria. Again, that one. So you see the animals and humanoids, they perish in the caves. And bones of animals, pebbles, and earth are conglomerated by limestone from dripping water. And then you get something like this. And some of these blocks are very complex, and it's not clear if there's anything of value in it. And preparing a block like this takes about between two weeks and 2 months, either by grinding or by using thinned acid. It actually takes a long time. So they gave us some rock. It didn't look precious, so you can have that and try it. And then we did the first radiography, and it looked like what? A pair of shrimps. Then it was a 2D virtual section of the 3D data set. And actually, we later also compared with X-rays. So on top is the X-ray image. Here we have the neutron image below. And you can see there's a huge difference in contrast for what you see. And maybe now you can even guess what this is. So when we did the first 3D images, we found that. We first thought it was a lower mandible. It turned out it's actually an upper mandible, upper jaw of what I will tell in a moment. So actually this is upper teeth and the skull is missing. So then the lady started working on this, and she did the complete analysis of all the teeth. It was like crazy. She especially looked at the dentine external surface and the dentine pulp and the animal. And she found out that this is actually belongs to an extinct kind of baboon, which is called Cercopithecus williamsi, which was a giant baboon. And this is more from Clemens Zanolli. Teeth are very important to look at because they're paleobiological archives, and they preserve information about the life of an individual from childhood to adult stage. And what we can distinguish is the channels of the pulp, the dentine, and the animal. And what we will see in a moment, these are special. I'll explain why. So X-ray started early on for this. You can do X-ray microtomography or even synchrotron CT, and most of the times that works perfectly. Sometimes it does not. Here's some segmentation from X-rays of one of those teeth. Here again, separation of all the different elements of teeth. And then we got this. On top, you see an orangutan. On the right, a modern human. And then a Homo erectus on the lower left. And on the lower right, what is it? Apparently, these samples have been on the museum storage for more than 80 years. And for more than 80 years, scientists have quarreled what it is. Is it human? Is it orangutan? They couldn't tell. From the outside, you don't really see any differences. So these are some sections later on from radiography or from tomography. This is a typical example of other teeth which work well with X-rays, but here in this case there was no contrast at all for X-ray microtomography. So we tried with neutrons. I hope you can see that movie. And even with neutrons, we got again contrast between animal and dentine. It's very well distinguished, actually. Okay, this is what came out of it. And you can see that the dentine on the inside has like different peaks, like a mountain landscape. And then we learned that these peaks here are typical for humanoids, for humans, and they do not exist in orangutan. So finally, this question was solved. This is an early hominid. Okay, now I would like to move on to paleontology. This is also some older example already, because our reactor has been down for quite some time now. There's nothing new. We are looking at mammal-like reptiles with neutron-computed tomography. So first thing I learned was that the mammals are actually older than dinosaurs. I didn't even know that, and their predecessors. Mammals coexisted with dinosaurs, and only when the dinosaurs were killed or extinct by the meteorite, then the mammals took over, but they have been there all the time. So these non-mammalian synapsids, this is the predecessors of the modern mammals, are important for the early evolution. But it's interesting to look at the skull, which gives us information about the evolution of respiration, sensory systems, and the brain and the metabolism, which I will show in a moment. So there's not much known because a lot of these skulls were found in red beds, which is iron-containing ores. And it's not possible to examine them with X-ray. So they are prepared on the outside. The skull is completely clean, but on the inside, it's still filled with that red rock, which is impenetrable for X-rays. So just a quick look, synapsids, this is actually defined by the windows in the skull, and they are different from the diapsida, which are these dinosaurs, anapsida, which is something like turtles. And on that branch of the synapsids, that leads eventually to the mammals. So looking at one of those skulls, either with X-rays or with neutrons, and what we like to learn is about respiration and sense of smell, then the metabolic rate, and whether the animal's warm-blooded or not. How can you tell that from a skull? And of course also the brain and the hearing. So this is typical human nasal system. They have nasal cavity and something called turbinalia, which is a sponge-like labyrinth. And this, as I will come again to, this labyrinth actually is used to moisten the air and to warm up the air. And that means it exists only in warm-blooded creatures, not in reptiles. Oh, here's one guy, Gonopsid, and you see the nose here. And these guys here, also reptile type. But in this guy on the right, we find turbinalia, which means this guy was warm-blooded. Here's some better cut of that. And that's also for a sense of smell and thermoregulation. So this is what I already said before. It's like thermoregulation and air conditioning, and also the reduction of water loss by breathing. And this is only in warm-blooded animals. And then let's look at the brain. The blue part is the brain, red part is the hearing organ. Find a lot of anatomical details. So I can even tell here the, oh, what's the name in English? The organ for equilibrium in the inner ear. You can see those canals. And this guy was actually kind of a mole who was digging. And again here, he found the bones for hearing. nose canal. You can find the stapes and the incus, the quadrate. What was interesting, there was no cochlea, real cochlea present. There's just a tiny tail on the bottom here, which later developed into the into the cochlea in other animals. And they also learned from that scientist that hearing actually developed from the lower jaw and not in the skull, because in the beginning animals would just lie on the ground, have their snout lying on the ground, and they could feel vibration like other animals trampling surround them and not much more. And let me see if there is one more here. It's more about hearing. And actually what the first sense of sound or vibration was therefore in the lower jaw. And later on it moved up in the skull, and the little bones in the jaw joint became free, and these are the hearing bones today. You can see some more. And I will stop with the hearing about here. There was much more measurements, and the guy was even able to calculate the frequency range from those measurements of what the animals could hear. But here's another peculiar thing. Tooth structure, something very unusual in some giant pelycosaurs. This is a typical tooth of maybe a mammal. Don't go into detail, it's just dentine animal, it's just a very straight shape. But some teeth have a very strange shape. It's called plicydentine. It's an infolded layer inside at the level of the tooth roots. And what it does, I will explain in a moment. Oh, it's this friendly laughing guy here. I had teeth like that. It's plicydentine. It's called labyrinthodont teeth. So this is all not done by me, of course. And we found evidence of this plicydentine in many here. Also on this guy, a pelycosaur that we examined here at FRM2. And even here you could find the plicydentine. Here's some reconstruction. And what is it all for? The plicydentine actually increases the surface of the tooth and makes them stick better into the to the jaw, because there's several ways of how animals have teeth. It's like just stuck with a smooth surface in the socket and pushed out by following teeth, or they will just go up sideways and stand up. Or here, some of those reptiles here. There's also the next tooth is coming, but for many of these, the plicydentine just increases the hold of the teeth in the jaw. So here, again, for this part, first record of plicydentine was found in this type of animals, Varanopsidae. This is a group of pelycosaurs. Apparently, it was more widespread than assumed. It was hitherto often not found or overlooked, because the plicydentine is, of course, in the tooth roots, which are inside the jaw bones. And one more example before I come to a closure. This is about reconstructing brain and vascular system in mammalian forerunners. How would you study the brain? The mammals possess, in relation to the body, the largest and most complexly structured brains among vertebrates. And the mammalian cortex is the most striking thing. It's actually what makes, think. So there's three different kinds of brain. The neocortex, the big part, like the humans have, the limbic system, and old reptilian brain. And trying to reconstruct the shape of that is less easy than thought. So first of all, soft tissue is not preserved. And we can only deduce the shape of the brain from the hollow space inside the skull. But the problem is there's also some other matrix, liquid matrix, and sometimes some parts of the cavity for the brain are actually open and are not fully enclosed. So again, neutrons. That it says that the brain case was only partly ossified. That means not all of it was bone. There was maybe a membrane or whatever held the brain in there. Looks like this, for example. So what you can see from the skull here, great parts of the brain were not encircled by bones. So it's difficult to say if that shape that we assume here was really the shape of the brain or just a hollow space. Maybe it was much smaller. There's some unfilled space in the brain case here. That was mostly, could have been blood vessels, for example. It could have been liquid of the brain. So this is not clear. Again here, what's the unossified zone? So we can only reconstruct the endocast, which is the hollow space in the skull. And this is probably not exactly the shape of the brain. So questions here. What was the unossified, the unbony zone here? How large was it actually? Was it already covered by a thin layer of neocortex? How did it all evolve? And how was the vascular, the blood vessel system organized? So search for a species where the brain case was well ossified. And for one where the brain was in close contact with the brain case. So you can see impressions of soft tissue structures in the brain case. That's a clue that it was in close contact. And we just looked at several ones. The Ictodonphilids had unfortunately a large unossified zone, but you can still see impression of blood vessels. It's just amazing what you can find. Again here, blood vessels. Here also blood vessels. So the hindbrain was apparently in close contact with the brain case. And we could reconstruct so far unknown parts of the vascular system. And okay, other different things, especially the unossified zone was apparently the terminal chamber of several blood vessels here. So this was actually filled probably with blood or the liquids. So I won't go into all these details. Another guy, Cavingasaurus fossilis. We try again with this guy. These are all bony walls. So this brain case was nearly completely ossified. This is a cut, of course, so you're looking sideways. Yeah, sharp impressions of the cerebral hemispheres in the brain case, like tissue imprinted on the bone. So probably there was close contact between brain and brain case. That's nearly completely encircled by bony walls, so we're quite sure about that shape. And the first evidence of a neocortex-like structure, as the other guy, Michael last told us. And before I complete that, I will stop here with those bones and brains and do a few final remarks for paleontologists. Of course, neutron radiation is many orders of magnitude weaker than synchrotron radiation. It takes more time. As they are electrically neutral, they do not interact with electrons or chemical bonds, as long as you have thermal neutrons only. That means you don't destroy stuff, because sometimes when people put something in a synchrotron, even especially the teeth, they actually turned violet just from the radiation. There was colorization. And other samples are also, biological samples are also often destroyed by synchrotron radiation because it's way too intense, but there's no colorization of samples for neutrons. For thermal neutrons only, there's not enough energy to generate recoil protons, which would really destroy chemical bonds, and they also do not destroy potential DNA for that reason. So far, thanks for your attention. Anybody still there at all?
Yes, we're still here. Thank you, Pukat, for your talk. Any questions from the house? Yes, we have a question.
Thank you for the talk. I would have a question about actually the last slide about the possible damage, because I had some fossils scanned at a neutron scanner, sorry, and actually we had to wait because the sample got activated, like became radioactive. So
yeah, that's correct.
So is this something common with fossils? Is this only the fossils that do that?
So about everything that you put in a neutron beam becomes activated. Some of that stuff for milliseconds, some for minutes. For typical fossils, we usually have to wait for some days, maximum 2 weeks, until we can return them. It's not an issue. Just a single time we got a rock which looked like Flintstone. I don't know what it was, and that became rather radioactive for a longer time, and we had to keep it for quite a while. So typically, we first irradiate samples in doubt briefly for a few seconds or so, and then we give them to radiation protection. They do a gamma scan, and then they can tell us exactly what's inside, and they can also tell us how long we can irradiate them to stay under the permitted limits after 1 or 2 weeks waiting time, so we can safely return them. So, and Some rocks even have natural radioactivity. So we actually have to do a measurement before we put the samples in the beam for some. And it only counts what we add to it. So sometimes even the natural radioactivity is higher than the limits that are permitted for samples to be released. But we can give them back if we don't add to this. So normally it's not a problem. It's usually just metals, cobalt and silver, which are critical in activation if you keep them in the beam for too long. If you have any other artifacts or objects of art, you should make sure to have a brief scan of those and not irradiate them too long. But for generally for rocks, it's not a problem. I mean, of course, iron beds, like these red beds, they contain iron, and iron gets activated, but it decays in a week or two, and you can return it.
Okay, a second question.
A related question, thank you. I just want to ask about carbon dating. Does it affect carbon dating at all? Thank you.
Yeah, my first answer had been it does not, because we don't do that. The radioactive carbon is created by irradiation from cosmic rays from the sun. I have learned in the meantime that there's actually a second path how you can generate C14 out of oxygen, which is rare. And it is possible to influence that, and we wanted to do more calculations on this, but this work is not published yet. So the answer is it may influence, but probably not strongly, and we have to calculate before we do that, so we know what we're doing. So if we generate C14, it's not in the way that it's generated by cosmic radiation. That's a different path.
Okay, we have time for more questions, if there are any. Oh, there's another one, Robert.
Thanks, Bukat, for excellent presentation. There were some questions for the previous speakers. I'm not sure if you got them or.
Oh, yes,
I didn't see the chat.
Yes, in the chat room.
Let me open that. So my chat doesn't seem to be working. It doesn't show me any messages. It just says that I can send a chat.
Oh, Chachi can read the question?
No, I cannot. I don't know.
I'm saying, Chachi, maybe can read for us.
There is one question, but this one is not for the current speaker. I think it's irrelevant. But maybe he might make a comment. It says, it says on the shape of memory alloys, is it possible to carry out spin resolved imaging for these types of materials? Are there any reciprocal space maps for neutron related diffraction? I'm not sure whether you'll be able to.
I'm sorry, I cannot answer that. This is
Yeah,
not my field.
all right, no problem.
Okay. Another question? Oh, we have another one from Sia.
So are there any initiatives that are being done to improve the resolution of the neutron tomography imaging?
But are there ways to improve resolution? Was that the question?
Yes, yeah.
There are some limits. We're actually working on that right now. The problem is always that you can detect neutrons only with a nuclear reaction. And that reaction deposes a lot of energy. So you have an event in your scintillation screen, which is several micrometers or even tenth of micrometers big. There's always many photons per neutron. So currently with thin screens from gadolinium with gadox, you can reach something like maybe 10, 12 micrometers. We're actually working on a new kind of borated screens, which have where the reaction than in the lithium or gadolinium, and it should be possible to reach maybe 2-3 micrometers. Actually, some other guys have also tried with gadolinium. They reached 4 micrometers, but then we get into a totally different problem. We don't get contrast anymore. because there's absolute, all these resolution measurements are done with gadolinium, which has the highest cross-section of all elements. And you can still distinguish edges at that scale. But practically, there is no element, no sample that gives you any contrast on a scale of a few micrometers, because there's simply no attenuation, no absorption enough to make an influence on your neutron beam. So I guess the practical resolution will be in the order of 10, 15 micrometer, because just the samples don't give contrast. One might just think about looking sideways into the membrane of a fuel cell, maybe, so that the sample is at least elongated in beam direction, so we get more material in the beam. But otherwise, I didn't find any application where you can really use a resolution of 3, 4 micrometers, because there's just no contrast.
Okay, thank you.
Last more? Okay, we have another one.
If one looks at your final slide there, it seems like one can use neutrons now for normal imaging of human beings.
No, this is not correct. The problem is the human being consists mostly of water, and we cannot penetrate 1 centimeter of water. I can find a sellotape on a block of 20 centimeter aluminium, but I cannot penetrate 1 or 2 centimeters of water. Just the high contrast for hydrogen is detrimental for that. And on the other hand, you would still do radiation damage to humans, because you're never alone with neutrons. You generate, on impact, you would also generate gammas, and those gammas would have bad impact on the human body. And if you're not on a neutron guide, you still get hard gammas, and you get fast neutrons, and they do damage to humans, so not a good idea. But actually, we use fast neutrons for cancer therapy.
Okay, I think we can thank the speaker once more.
Thanks for having me.
We are done for this session, so we can go to lunch, and we should be back at 2 o'clock so that we can convene with the discussion session. Thank you very much, colleagues.
Yeah, while you are going for lunch, you can just watch on the screen for yourselves. I'm sure the photos will be available for everyone to download.
Hello? Is this connected?
Hi.
Hello?
This is Mark Johnson.
Hi, Mark, but I can't hear him.
You can't hear me?
Yes. Hi, Mark.
Hello. Let me check my audio settings, test mic.
Screen.
I can share my, okay.
Let's get started.
Hello.
Okay, he's there. Okay, this one.
Hi, Ralph.
Hi, Mark. Nice to meet you.
You too. Last time was Taiwan, I think.
Correct.
Before COVID.
Exactly, my last trip.
Are you?
Yeah. I've been busy traveling this year, but yeah, it stopped us for 2 years. So that's saving the planet.
Okay. Need a microphone for him, no? I'm going to take this one.
Okay. Good afternoon, everyone. Welcome back, and I'm pleased to see that there's so many people still present. Okay, so we have a discussion session now, and there's a number of things we want to try and get consensus on, and ideas we'll want to run past you. So I'm very pleased I see Ralph is still connected. So Ralph, thank you very much, and Mark is there. Thank you very much, Mark, as well. So both of you could possibly, sorry for the impromptu request, Ralph, I don't think you're prepared for this, but it's nice to drop the bombshell on you. So if you could possibly give a very brief discussion of how you handle your user program at your facilities. Because that's something that, of course, some of our colleagues would have ideas and experience in that, but we also have a lot of people that are inexperienced, and this whole concept of users are quite strange or quite new. And it would help a lot if you can just set the background of how this is typically done at 2 major European facilities. So can we start with Mark, or
Yeah.
Can I ask you, Mark, to let the
Yeah, sure. Perhaps I've had a little bit more time than Ralph to prepare, so let me share my screen, because you sent me a list of points that we could cover. Okay, so this is just, so I've put a few slides together, and I invite Ralph in particular to add or contradict to anything I say, but also people in the audience. And as you say, Andrew, this really should be a discussion session. When I was putting these slides together, let me just get a pointer option. I thought of this Brightness 2 that you know very well, Andrew, this project and the document that I was involved in producing about the neutron landscape, mainly in Europe. But it's, I think, with respect to the workshop you're holding, it's a document that's highly relevant, and it's very recent, so it's certainly up to date. So that's just, I'll leave these slides with you. And so anybody's welcome to pick up this link and look at that article. So these were the points that you asked us to sort of comment on. And so I'll just go through them one by one. And where I've put a red arrow, I've got another slide. And so the first one is the user community, when and how did they establish themselves? And so that's a sort of a historical perspective. So the slide I put together for this is here. And this map's taken from that document that I've just alluded to. And it shows the 4 major operating facilities, ESS under construction, a couple of smaller user facilities in Prague, Czech Republic, and Budapest, Hungary. some even smaller reactors still operating in Poland, Austria, Delft, and I guess this is Germany. But where you see these crosses, this is where facilities have closed down. And so notably Norway, Berlin, LLB, Portugal. And the point of showing this to you is that in Europe, we used to have a very rich ecosystem of research reactors. They were often designed and built for materials research. And so they were a base for expert users. And I think when I was thinking about this point, I think that's the historical origin of the user community in Europe. And ILL, as I mentioned on the right here, on the left here, was actually the first facility to be designed as a user facility and to have a whole set of neutron guides to serve a wide range of instruments. And to develop the user community further at ILL, I mean, our user community has sort of two aspects. First of all, there's all the users that come to ILL, and most of them come from the so-called member countries, and there are 14 of them. They're the countries that fund ILL, but ILL's not exclusively for scientists from member countries. So there was outreach to member countries in the early 2000s, and that increased the membership from 3 or 4 long-standing member countries to its current value of, where we have the 3 associates, France, Germany, and the UK, and 11 scientific member countries. And since then, it's a continuous effort to reach out to the user community, either in the form of new scientific member countries or new communities. Science is evolving. We want to bring in new communities. And there has been a trend, I've put here, from expert to non-expert around all these facilities. There were expert users. But as science has become, research has become sort of multi-technique, then people essentially don't have the time, the bandwidth to become experts. So we sort of have to open up more and more to non-experts, which I think is a very good thing. And there is a trend, the experts historically were physicists, and then the community's grown into chemistry, which is probably the biggest community these days, biology, engineering, material science, all the sorts of things that have been covered in the workshop over the last 2 days. So that's a sort of an overview in Europe of how the user community has developed. And I think if I go back a page, then what I've said there in this continuous outreach, a very important aspect of that is the conferences and workshops that we organize at our own facilities like Munich and ILL, but also going to other conferences, for example, soft matter conferences. We heard about geoscience yesterday, geoscience conferences, energy materials. We need to go to those places that aren't neutron-centric and sort of and promote neutrons in these sort of new and wider areas to bring in to bring in new users. So that's what I wanted to say about developing the user community or its historical origins. I don't know if there's any comments already on that, or I can go to the second point, which is how many members and typically how they vary across the country and countries. So,
any inputs here?
Yeah, I would like to add something. First of all, I think Mark has summarized everything very well. So I have only 2 remarks, which maybe also fit in and add the comments. So the first one is, I think you have decided for Safari that you want to use neutron diffraction, neutron imaging, and small angle neutron scattering. So I think exactly these 3 methods have really 3 benefits. The first is that you get a high number of publication This means this is exactly the three methods where you can easiest build up such a user community, and they are all related, these methods, to industry too. So that means these three really combine all the things which you need for a good start when you build up a new facility, because you can contact in the easiest way the users. My second remark is, I think what we should also consider for this instrumentation is sample environment, because sample environment attracts the user, or users bring their own sample environment to the facility, and then they can do what they like because they have already prepared their topics. So the sample environment is very important to attract the users and to build up the community. So I think these two remarks will add what was already mentioned here. And this is a very important point when you think how to start to build up the user community, because you build up your instruments not for your own, you build it up for the users. And if the users are involved strongly, then you have a very good opportunity really to get them at your facility and then to do common projects. That was my comment on this.
Thank you, Ralph. Yeah, so very important. I mean, I've trying to communicate this to my team as well, that ultimately, of course, the instruments have to be technically specified, but we can't really do that in isolation. You have to do that in conjunction with your user community, because they need to come back and say, what are the specific requirements regarding instrument capabilities, as well as the sample environments and other support systems like software, data processing, and so forth as well. So therefore, yeah, the involvement of the community is very important.
Yeah, one comment. Users will not ask about the instrument in general. They ask about the sample environment, what they can do. They have a problem and they want to do something with the sample. They do not ask about the resolution of the detector or what you can do. That is really behind all this. The first issue is the sample environment, what they want to do. And then you get them in contact and then you can make progress. Yeah.
Okay, just a general question then. What is your predominant requirement for sample environments at your facilities? Is it mostly temperature, or is it more exotic than that?
So in our case at MLZ, it's a huge variety, because users come from so different fields: medicine, chemistry, physics, geoscience, and so on. And it is also changing because the user community is also changing, and there are new trends. You have seen all these contributions from batteries. 10 years ago, nobody was interested at all in these things, but now everybody likes to do something to integrate a potentiostat at your instrument and to use special sample holders and so on. So that has really changed, and there are other trends. So it is not to say, okay, we fix on this, and then you will see the users are coming. No, you have to listen what the users are doing, what they need, especially in situ operando. These are the two keywords, yeah, where neutrons have this huge benefit to get all the information from inside.
Thank you, Ralph. Mark, do you have any suggestions from your side?
Yeah, I was, the same answer. I mean, ILL and Munich are very similar facilities. Sample environment, first of all, it's hugely important, yeah, and you have to invest significantly in it. It's no good having the instruments if you can't put the sample on the instrument. Every instrument has variable temperature capability, from 2 Kelvin up to at least 600 Kelvin. But then on top of that, there's magnetic fields, electric fields, high pressure, humidity, for mechanical engineering applications, stress devices and so on. So it's extremely diverse, and it's almost open-ended, really. But a hugely important area. Another comment I was going to make with respect to what Ralph said and highlighting those three techniques: powder diffraction, SANS, and imaging. I think that really is the best place to start, and it's a real foundation for getting going in terms of bringing in users because of the high throughput. But also, and this is the point I'd like to emphasize, is that each of those techniques has a direct equivalent in X-ray scattering. So, people will be familiar. And actually in labs, you can have lab powder X-ray diffraction, lab small angle scattering, and lab X-ray imaging. So without even going to synchrotrons, people will already know about those techniques and step more easily into them with neutrons. And of course, they have their equivalents in the synchrotrons as well. So they were the two points I'd like to follow up on what Ralph said.
Okay, Mark, so we've got a question from our floor, from Jitesh.
Oh, okay. Thank you, Mark and Ralph. I just want to ask a question about bringing new users on board. Do you think, based on of course, you have an established user community in Europe, but who brings new users on board? Do you think the user community themselves, through their papers and research, bring new users on board to your facilities? Or do you think that your outreach as a facility brings more users or new users on board? That's the first part of the question. And secondly, what kind of outreach do you do as an organization? Do you need to do this, or I guess you oversubscribe, so you don't need to do this, but maybe you could comment on that.
Perhaps I'll start because you said something that I find slightly provocative. But let me first of all introduce Giovanna Cicconiani, who's joined us, and I can see her here. So Giovanna Jitesh, you've met Giovanna recently. She runs the user office at the ILL, and she'll show a few slides about how our user office works in due course. The point I wanted to sort of come back on there, Jitesh, which I say is slightly provocative, is yes, we have over demand, but it's hugely important to keep bringing in new users. The expert users that developed neutron scattering 50 years ago at the ILL and at the German facilities and other facilities in Europe, they've retired, they're retiring, and they have to be replaced with new users. And so we can't just sit back on our laurels and expect these new users to come in. These are our if you like, if we were running a normal business, they would be our clients, but they're certainly collaborators and they're partners. And so, they're more than clients. And the point lower down here is that the users are absolutely crucial to our facilities. Without the users, we don't exist. And so we have to be proactive and intentional about reaching out to new users. Your comment about publications is very interesting because, that's clearly one channel and vector for promoting what we do. And actually, and Giovanna's been running this for many years, we have, like most facilities, a strong communication activity, not only to, so we don't just rely on people reading the journals, but we try and publicize, these important pieces of work in various other magazines and of course websites, social media, and so on these days. So we have to promote the published work like that. But the workshops that are in these points, I mean, they are a very good way, and so of reaching out. So I mean, we organize lots of workshops, and it's the same across the facilities. And they are ways of bringing in new users, but we are, to a certain extent, in those workshops, preaching to the people who know about us. So it really is better, as I just tried to say, or essential in addition to, go to energy materials, go to engineering conferences, soft matter conferences, biology, cultural heritage, and be brave and address an audience that doesn't know neutrons. And so there's many aspects to outreach. It's really, really important to do it, and to do it seriously is probably not the right word because we all do things seriously, but be intentional, strategic about it, and try and measure the effect. I mean, Giovanna in the user office counts very carefully the number of new users we bring in, and so it's hugely important.
Yeah, if I can add something to what Mark just said, I think that outreach is certainly important, but it's true that proposal submission is the starting point for an adventure, if you want, but it's also the ending point of a collaboration. A key issue to bring in new users are the involvement of the scientists at DLL who are ambassadors to conference, which are non-Newton conferences. This is very often much more effective to bring in new people. We have been through an exercise recently. Mark was part of the team during a European grant, which allowed us to do roadshow, workshop, identify new community, new countries. But at the end, what it counts is some scientists that convince you that neutrons are useful. Access mode is also important. You don't need and you don't want to wait 6 months to have a proposal deadline with a lot of expert users who are competitors. So if you have an access mode which is easy, fast, and less competitive, this can help new users to test their scientific case and brought in, I would say. The problem is complex.
Thank you very much. Now, before we move on, is any inputs from the floor? Just a moment. So Dr. Danny Adams has want to pose a question to you.
Thank you, colleagues, for the contributions and the sharing with us your experiences on that side. I think for me, and I make mention of that in my presentation yesterday, is the whole issue of sustainability. And in the discussion of users also, I think that's one of the elements which will determine sustainability in terms of a stable user base. So my question is now, what are the guiding principles now, apart, because maybe in Europe it's different now here because people have been exposed to this kind of techniques and find a way now to do their experiments. But in the case of South Africa, where it's not completely green fields now, but we have to build a strong user base that can be sustainable into the future. And I don't hear in your contributions now that you talk about the research agenda that should be key to key underpinning, because if there's a clear research agenda, clear priorities that you and areas that you want to pursue now here, that in my mind will keep the users over a longer period of time. So a user base that you're talking about, new users, are they sort of very dynamic and your numbers are changing, or do you have a stable base that you basically driving the agenda for your particular institute? The second point I want to just check with you and is around your access models. How do you, the users, are they paying subscriptions to use your facility at the point of entry, or is it that they, through grants now that jointly developed by the institute, they can then access the facility? Because in the case of South Africa, the model is that researchers get a grant from the funding agency now here, and they probably have to pay excess fees to that now. And that's in some cases or in most cases, the limiting factor, because the charge out rates may be completely or much more than what that they can afford to. But also, in the case of Nexa, which have this facilities in place now, it was not an open access situation now here. It was difficult for universities to use the facilities because of the environment in which the infrastructure sits now here. So how do you overcome some of these access challenges, and what's your model? Thank you.
Who wants to start?
If you want to add comments.
Maybe I start.
Yeah.
Okay, first was the question if we have a kind of a agenda that we focus on special fields and topics, what we are doing. I think, of course, there are a few fields like magnetism where neutrons are unique, which has a tradition that this is always a topic which is running on the institutes, because we have bought very high expensive magnets to run the sample environment, and this was also in cooperation with many groups. And also, I think the topic energy is strongly involved in all the facilities. There are a lot of examples in recent time coming up, and you can support also industry and do something for our society. Yeah. But of course, you have to be always open to other issues. That is what I said at the beginning. We cannot say we have these 3 topics, then we will lose a lot of clients who will say, okay, that's not my topic, so I'm not interested to continue such measurements. So you have to bring a focus, of course, because of the tradition and also of the strong input Newtons can do, but you have to be open for new fields. You see quantum optics is now coming up, and new topics, and you have to think what you can do in this field. And then, of course, you have to do actively advertisement, to go outside and then to talk to the people and then learn what are the problems. This you have first to understand, and then in a second step, you have to provide something what you can do to support them. So that's for the first question. The second question was with the grants and how we can reach the people. So in Germany, you have the possibility to apply at the government or at the, for example, here in Bavaria, in our special area, also fundings. And then you have, together with universities, the possibility to apply money or funding for instruments to build up, to get money for traveling, doing the beam time, and so on. And also the facility itself has the possibility to apply for projects which are required from the user community. So we cannot say we like to do this and this. That is not sufficient. We have to support this with user information, with common projects, and say the user community needs this and this. There's a huge request on this. And then we start to think about how we can provide this instrument or the sample environment. So we get not the money for free. We have to do actively things with users, with the community, to make improvements and to stay not always on the same status, to have improvements, to go further for progress and also new instrumentation. Because you can also not keep your instrument for the next 30 years. This will not work. You have to make changes. You have to bring new issues and so on to make your facility attractive. That's from my side.
Ralph, could I just ask just a follow-up question? So can South Africans access your facility on peer review? So you've got 2 calls a year. Can they submit calls or proposals? And would they be successful without being a member of your facility?
So in our facility, yeah, in Germany, it's worldwide open, so we have no restrictions. You can apply from everywhere you want, except at the moment from Russia. Yeah. But all other things is possible.
Yeah, so the access is then provided on peer review of your public
of your proposal. It's also possible to buy beam time. If South Africa, a mine, is saying there, oh, we need this urgent, we need this beam time, you can buy the beam time. Yeah, that's not a problem.
Yeah, it's 7,000 euros a day. It's very cheap for us, actually.
Well, I can tell you, for many companies, this is not the main issue. Because if they solve, you have seen this example of pipeline clocking, yeah. There we are talking about a few 100,000 euros you lose, yeah. So they said they can pay many days. This is not the issue. They want to solve it. Yeah. So it depends what you are doing, of course. Yeah.
Okay, so just to clarify, Ralph, so a person from South Africa can apply for beam time and they can be successful, but they're then responsible for their own costs, travel costs and accommodation, but no costs for using the facilities on your side.
Yeah, that is. And of course, if you have to publish. If you do not publish, then you have to pay for the beam time. Yeah.
Yeah. And then in principle, in the longer term, we could apply possibly to the body you referred to in Germany, and in that way try to get financial support, if I understood you correctly. Or was that only for German users?
What I mentioned is mainly for German users, but there are projects, and I've heard there's also a project between South Africa and Germany that people can make some exchange program where people can traveling to each country and work in scientific topics together. Yeah, there's also such a project. This is called DAAD, and this is an exchange program from German scientists and foreign scientists, and that is too many countries.
Thank you very much, Ralph. Mark, we have
Yeah,
other questions as well, so let's just finish this discussion.
Yeah,
So Mark,
I just had a couple of points, and first of all, so ILL, South African scientists can apply for beam time at ILL. The majority of beam time at ILL goes to the funding countries or scientists from the funding countries. But South African scientists and any other non-member scientists can be part of experimental teams from the member countries, or can apply in their own right, and there are various criteria for accepting those proposals. If the science is excellent, the ILL, like any facility, wants to do excellent science. So we're all open in that respect. One point I'd like to emphasize, and I think that's what you were touching on, Andrew, is that the facilities are free at the point of entry. So nobody pays except industry for proprietary research to have access to the beam time, and at least in Europe. And I think that's really important, especially for you in South Africa, where you want to build up a community. And if you're investing significantly in a new facility, then the worst possible thing would be to have people not able to come because they haven't got funding from research funding organizations that allows them to do their neutron scattering work. These facilities are expensive, and we have to sort of remove as many barriers as possible and simplify the access so that you can bring in as many users as possible and the best science, and effectively, in your case, continue to grow the community. So free at the point of access, I think, is really important. Paying travel costs is a smaller cost, but I'm not sure how it is at Munich, but at ILL, Giovanna, her office, covers the costs of all the users from the member countries. So not only do they not pay for beam time, but they don't pay for travel or accommodation when they come to us either. So it's I wanted just to echo what Ralph said on the first point, which is sustainability in terms of adapting to changes and evolution in the scientific community, in the research world, and the societal challenges we have to address. We all have a mode of operation which is sort of bottom up, really. The user community brings the scientific problems. We have to promote what we can do, and then they have to bring their science to us. But there's a point that sort of comes later, but we can talk about it now, which is how we address these sort of common research themes in the most effective and efficient way. And as Ralph was sort of suggesting, not only do we have to be open to these new research projects, but then we have to make sure we provide the appropriate services, so for the appropriate sample environment and other ancillary equipment and services that ensure we can do successful experiments. But then there's another step as well, which nobody's really done yet. And the point lower down is, do these users cooperate with each other? And you could imagine, since all the users come to us, that those are, for example, interested in energy materials, that we become the facilities, and in your facility in South Africa becomes a natural focus point for collaborative research between interested groups. And that's a step that, we call it thematically driven research, and you might call it top down compared to bottom up, or you want a mix of both of these sort of approaches. And the idea is that you would, by encouraging collaboration and providing the necessary support services, you would generate added value and more impact from essentially the same number of research groups, and make better use of your facility. So I think there's a really interesting point there going forwards in terms of sustainability and cooperation between user groups, which it comes lower down on these points.
Thank you very much, Mark. So if I can just add a comment. So these facilities are actually research enablers but your research programs are actually defined by your users. It's
Yeah.
not that you can, from your facility, emphasize our focus is on lead batteries. The focus is on agriculture. That comes from your users. They utilize your equipment, which could potentially address their problems. That is the right approach, is it?
That's the current
could be one
approach.
model.
That's the current model, and it's the same everywhere. But there is this discussion about how you support thematic research and how you sort of maximize your impact in certain areas. And so, I mean, naturally anyway, we tend to favor certain areas of research, if only because of the interests and skills of our scientists and the sort of equipment that we're able to put in place. So, and actually that's a really interesting difference between the facilities. We all offer similar instruments, you know, with around our sources, but some of the things that are developed specifically at different facilities depends on the scientists who work there, and that's why, you know, it's not a business client interaction. It's a real partnership and collaboration between the facilities, the facilities, and the user community. So yeah, there's lots of points in there, but so you're right, Andrew, in what you say. It's exactly as you say at the moment, but there is this sort of ongoing thought process and some action towards better supporting key areas of sort of topical areas of research, and having an evolving process so you can follow changes and even drive changes in research.
Thank you very much. Dave, do you still have a question?
Oh, there it comes through. It's more a question, a comment on how to, I think we have to go about developing a user community. And it spins off from my experiences over, well, it's now decades, trying to and eventually getting to synchrotrons and that user community. And a big part of it hinges around schools and learning expertise and training. So it is workshops in schools to develop the expertise in the next generation of user that can appreciate what they need to do. They also then become a significant part of the workforce. This is something that became apparent during lockdown, is that suddenly when things just ended up being mailed into beamlines, these poor beamline scientists ended up overworked, burnt out, and whatever. So the users are a significant part of the workforce of actually getting the work done, and they need the training. Now, it's a big jump from I want neutron scattering on my favorite XYZ to being able to get to where I can write a coherent proposal that will stand up to proper peer review and get you a successful access to the experiment. And it's a bigger hurdle, well, than I originally anticipated. And I think we need to invest time to develop people in there, time and energy.
Yes, that's a very good comment, Dave. And hopefully we can discuss that a bit further just now about modalities. How do we physically build this community? Mark and Ralph, just want to add anything else? Or I think you said there was still continuation of your topic, Mark? Or you finished with your discussion?
No, well, with respect to the point that's just been made, there's some really, really interesting points in there. All of the facilities run, we participate in workshops and conferences internationally, but we run our own workshops. But not only, some of those are schools, and you're absolutely, the question from the floor is very good. You know, we have to keep not only reaching out to new users, but ensure that we're training young users or new users. So lots of that training just happens because, you know, groups bring in new PhD students, and there's a natural sort of training process there. But we are intentional about running different kinds of schools. So we had one earlier this summer, just as an example, with the EMBL, the European Molecular Biology Lab, who's actually on site here in Grenoble. And that was a small angle scattering focused workshop that happens every 2 years, I think. And that's just one example. So we do those schools. And what I've mentioned on these on the points on these slides is that the national user communities, they have different ways. They have user groups, sometimes combined, as I mentioned yesterday, with the X-ray users as well. And that they have national annual meetings, typically. But also some of them, not all of them, so it's not a rule, but some of them recognize the importance of schools and organize schools as well. So there's what we do from the facilities, and I think it's a point we're going to come on to, is how the user community organizes itself slightly independently of the facilities and ensures education continuity and so on in the user community. So schools are important. They're organized in different ways. And 2 more points. One is PhD students. PhD students, I estimate they're about half of the people who come to do experiments. And because the PhD lasts for 3 years, there's a natural turnover. And actually at ILL, we measured that 60% of our users in 5 years are new users. And a lot of those are the PhD students. So there's lots of sort of training and education going on there. And those PhD students come back as, principal investigators and so on in the future. And the point about mail-in is, that's a really interesting one, because remote access is something we had to do, and it worked very well, actually, but it did put a huge burden on us. But it's essential that users who, as I say, are really collaborators, come to see the facilities. They're impressive facilities. They learn about what's at the facilities and the opportunities. But also what you don't get from mail-in is you don't get to meet the people and build those important human interactions, and which are the basis of then, fruitful collaborations that last many, many years. So mail-in, it's a great thing. It's a great option, as is remote access, but it comes in addition to this sort of fundamental way of working, which is coming to the facilities and meeting the people and contributing to the work during the experiments. So.
Okay, thank you very much.
2 points. Yeah, I would like to
proceed now. I've is there someone else? Sorry.
I would like to add 2 points, which I think match what Mark has said. So, of course, there are also new issues like robotics, like machine learning. All these things have to be integrated also in instrumentation. And this will be driven by the young people, because they know these things much better than the older ones. Yeah. And so that is something which is really important. Or what we have now started is to bring many instruments in a digital twin. Yeah, that students can really run the experiment as a simulation, and then to see how things are running, how the instrument is moving, what you have to consider, what you have to do, and so on. So these things are mainly really driven from the PhD students, who are more in favor to do such kind of work than the older ones. Yeah? And that is also something you have to make this continuously progress. Yeah.
Thank you, Ralph.
I don't know. Apologies. I don't know who to ask this question to more, whether to the floor, Prof. Pulling and Dr. Adams, as well as to Ralph and Mark. Is the user community concept unique to synchrotrons and neutron scattering facilities globally, especially from Europe, or do all other facilities or shared facilities have user communities? And then for our South African colleagues, do we have user communities around our shared facilities? For example, Itemba Labs is an example, or are the users very disparate and just on their own accord decide we want to use a particular facility? Because the whole concept of the user community, when I got to learn about it, was quite, I'm in the neutron scattering field, because these are shared facilities, these user communities established themselves. I don't know which came first, the chicken or the egg.
So it's a tough one, but I just wanted to hear your perspectives on that. Thanks.
Okay, anybody, Mark or Ralph?
I think the I don't think the user community aspect is unique to neutrons or X-rays. I think it's driven by the fact that you have a central facility, and that you have the user community. I say again because it's really important, is a partner to that or those central facilities. And they have to be organized around and with the facilities. And I was just wondering what other examples might be that aren't neutrons and X-rays. And if you think of the astronomy community, for example, and that's something that's important in South Africa, you're hosting a large part of the square kilometer array. Not nuclear, I'm trying to say CERN, that type of high energy particle physics. Their central facilities. What's perhaps, compared to those two examples, what's a little bit different for neutrons and X-rays is we don't have a single scientific focus like the astronomers. Maybe I'm not being fair to them, but they have a clear focus on stars in the sky, and particle physics is the same, whereas neutrons and X-rays, we cover everything, as I said earlier, physics through to biology, engineering, to cultural heritage, and so on. So that's perhaps a unique aspect of our user community. It's scientific diversity, but the central facility-driven aspect would be common to the astronomers and the particle physics people as well.
Thank you, Mark. Yeah, I'm sure Ralph is also in agreement with that. Okay, so
I totally agree with Mark, completely, 100%.
Thank you.
Thank you, Ralph. Yeah, so I think I prepared a presentation. It was very impromptu, so there might be a lot of errors in that. If we could just display that, so that we have a bit of agenda, and we proceed with the next hour to try and maximize our interaction and information exchange. Okay, that looks a bit strange. That's not the way I did it, actually. Next. Oh, sorry. I need to find the sweet spot again. Is this switched on? It's on.
And Andrew, can I just ask, will there be a chance for Giovanna to give a quick presentation about the user office at the ILL?
Jitesh, can we proceed? Yeah, we can proceed. Yeah, please.
So Giovanna can do that now, or?
Yes, please proceed.
Yeah. Okay, Giovanna.
Okay. I'm joining you. Do you see my screen?
Yeah.
Yeah. So I don't want to take too much of your time. I'm not sure what have been already said previously, so I will be going quickly through certain slides, which is a presentation which I already presented to you, Jitesh. So for those who doesn't know ILL well, where it's a European neutron facility, which is in Grenoble, France. The business model that we have is peculiar to the European or international facility. We have founding or member countries which participate to our annual budget. And of course, these countries, these members have a privileged access to the facilities, although, as Mark pointed out, we are open to excellent science from everywhere. We are operating a continuous neutron source on the form of a high flux reactor neutron source of 58 megawatt. These neutrons feed about 40 instruments. DLL is a senior institute because first experiment were carried out already 50 years ago. We are a relatively small facilities with about 500 employees, and in normal conditions, we provide about 150, 160 days of neutrons every year, which allows 1,200 experiments with about 2 users per experiments coming to the facilities. And the output is rather steady over the years at around 600 publications per year. I don't know if this flow chart represents how the proposal round and proposal submission systems works. I don't know if I needed to spend a lot of time on that or not. Cut me if it's something which is trivial or already touched. Can you see it, by the way? Is that better?
Can you go, if you do Control L, I think you go into full screen mode. Yeah.
Okay. Everything at VLL starts with, well, in principle, everything starts with the proposal submission, which is obviously electronically now since years. But as I mentioned to you before, this is the entry point to the proposal round, but it's certainly not the first point for a team. The team is gathering before, and we strongly recommend our users, even new users, to get in touch as soon as possible with our scientists to prepare the proposals. DLL is an European facility, is not a national facility, so the competition to get beam time is particularly high, and it's not only the excellence of the science which counts, but obviously also how this is presented, because what we ask to our users is to demonstrate that the neutrons are essential to their studies, and that the answer that they will get will be published, hopefully in nice papers. So the proposal preparation is a very important process, which is often done in collaboration with our scientists that very often are part of the team, experimental team themselves. Then when these proposals are collected and gathered at the ELL by the user office, before starting the actual scientific peer review by external panels, we have a technical internal assessment carried out by internal scientists, engineering, safety officer, because we want to be sure that the proposal can be technically done on one of our instruments and safely done, of course. Also, this technical review is very important to flag particular items. For example, if the request and beam time can be optimized down to a reasonable number of days, whilst keeping the minimum number of days necessary to do a proper experiment, and optimize the sample environment. Ralph was mentioning when I joined the meeting that in fact, yes, users very often do not know all the technicalities of the environments and potential offer that we can offer them. So this is the stage where we address these things. Yeah, we might also decide to propose a similar instrument to this proposal if the chosen one is particularly overbooked or for other reasons, and so on. Once this review is done, and I might say in parallel, we have also a scientific review, which is done by panels, external panels. So we have at DLL, we organize our proposal review into disciplines, research areas, and what we call subcommittees or internal colleges. So we have for soft matter, biology, magnetism, and for these areas, we nominate a panel with about 10 experts, which will read the proposals submitted to their disciplines, grade them, and then meet at the DLL. Actually, they will meet here at the DLL next week. We have a 2 days meeting planned for next week. Okay. And they will decide together which
Giovanna?
are, yes?
The connection is a bit bad. Maybe you can just go a bit faster.
Yeah.
I don't know what's wrong with
Yeah.
on a Friday
Well,
afternoon.
we have this scientific review, and in fact, these people decide which are the best proposal from the science point of view. And then the final allocation is done once the ILL management do what we call the national balance. As I mentioned at the beginning, we are a national facility and an international facility, which is financed by member countries. So we want to make sure that member countries receive an amount of beam time which is proportional to what they contribute to our budget. This is what the national balance count for. I'm afraid it's not very scientific. Well, it can be scientific, but it's not based on science. And then once this is done, basically we launch the experiment planning, scheduling, invitation of the users, so far and so on. Experiment can be done remotely, of course. We are equipped for that, but I must stress that so far, DLL is not promoting a fully remote access mode. There are reflections going on these fields, of course, but as Mark mentioned and Adam mentioned, we like our users to come to other facilities. Yeah, everything is done via our user portal, which is allowing everybody to do basically everything connecting to the user program. I don't want to spend a lot of time on that. If there are questions afterwards, I can come back to that. These are really technicalities about how we have set up our database and our interfaces, so I think I can skip it. Let me focus for a couple of minutes of these important slides. Access mode is very important, of course. So I just mentioned the proposal submission and the peer review system that it happens twice a year here at the DLL. This is what I'm calling standard proposal submission, which is external peer reviewed, and it's happening twice a year. But of course, we have other ways of accessing beam time to have access to the DLL. You might maybe have a look into details to this page afterwards. In particular, I want to stress it is very important to have fast access modes, because for new users, of course, but also for topics which are hot topics, as we are usually call them. So at the DLL, we have some routes for that. The easy route is a way to submit proposal and also sample, by the way, because for this part, you are not coming for DLL, it's a mailing link system. You ask for a very small amount of beam time, not to perform a full experiment, but just to test your idea, an instrument, a measurement, or whatever. And this is the easy access. You might have a full experiment, very important hot topics that you want to realize and to perform before the next deadline. So this is director discretion time. I'm afraid DDT is not a very nice acronym, but well, this is a very fast mode, which is not externally peer review in a sense that it's the director that decides at the end, but of course is not deciding alone. And very often the panel who are peer reviewing the standard proposal give advice. You can do test experiment, and of course also industry proprietary beam time is occurring very fast. So multiplying the access modes to be agile is very important. We have a bunch of policies, of course, that user needs to comply with. Scientific data policy basically deals with publications and how to record the data. DOEs are very important for tracking down the publications. User access policies is equally important, and in fact, the European community that drove these needs. And of course, everybody is familiar with the personal data protection policy. Remote access is something which existed at the DLL before the COVID pandemic, of course. We must admit that it was put in full swing by force on this pandemic, which is a good thing because now we are equipped to run experiments remotely. We are also training new users remotely. We have been through a long shutdown here at the DLL without neutrons for more than 1 year. This has not stopped the activities. So this is important to offer remote access solution. But as I said, for the moment, it's not something which is automatically offered, for example, on certain beamline or application. Okay, what I can say without entering into too many details, well, I think I can stop here and answer to your questions if there are.
Thank you very much. Thank you, Giovanna. I think that remote access thing is what impressed me quite a lot when I was there. Basically, from anywhere in the world, you can see your experimental data real time as your experiment is going on. So even though you can ship your sample in, you can quickly analyze or see your data, the raw data as it's been captured, and it's available for an indefinite amount of time. And you need to be able to publish, I think, within 6 months. Just remind me of that 6-month rule.
Excuse me, the 6 months for the proposal deadline?
No, for publication.
The publication, normally we have done some statistics. We have a gap between proposal submission and publication of about 2 to 3 years, depending on the publication. You must consider that now neutrons are very often used as not a unique technique. So, well, to compile a publication might take some time. But from proposal submission.
Yes. Okay, thank you very much. Yeah, let's move on to the presentation I presented. I've prepared. Hopefully it's much better. Yes. Like I said, this is just, as I said, something I did impromptu, just to, so we have a bit of an agenda. So the first question, or the first request is, please revisit the online questionnaire that you completed during your registration. It's just to see if your views have changed over the last 2 years, 2 days or not. And that is very important to us because that was the background that we tried to sketch with the presentations we had, just to illustrate what is possible. And in many cases, the authors or the presenters did indicate what instruments they used. So you could possibly make a better link to what your research interests are, and if there are other instruments that could potentially be of value in your research. Okay, so that's the first point. So ultimately from that questionnaire, what we want to determine is the instrument needs as part of the questionnaire, and then also determine the sample environments, as you've heard Mark and Ralph has reiterated a number of times, that this is an essential component of a neutron scattering center. Measurements are not normally done just at ambient conditions. There's always some parametric type of investigations. And what we have at Nexa is, of course, the temperatures. So we can cover the temperatures from 1.5 Kelvin to 1,800 Kelvin. So we don't have the other exotic magnetic fields and electric fields. But of course, if there's a need, we then need to motivate, and we should see if we could possibly procure equipment like that as part of the National Innovative Equipment Fund or one of those modalities. And they are very, very fancy magnet systems. It was not part of these discussions, but in a neutron environment, you need a very, very specific geometry of magnets. It's not a conventional electromagnet. In most cases, it's a split coil type of configuration, because you have to get your beam through the magnet. So what they do is they split the north and south poles, and it's normally superconducting magnets that are used, as well as these magnets are normally used, driven in a continuous mode, using a dilution fridge, or no, sorry, a closed cycle helium adiabatic expansion system to cool it down. So you don't use the cryogen, but it's all automatic if you do it with a helium-based system. Okay, so the sampling environments are very important, and please revisit that question as well on the online portal or the website. Then, of course, we need to determine the user support systems, and this was the discussion we just had now within the last hour. Online portal, it's very important that there needs to be a link, and that goes like through a user office, like Giovanna has indicated. Then what type of modality for access is required? The reason why I'm putting that on here is that we've had many long discussions with our management at Safari. Of course, I know you're not exactly in that role anymore, but you're still an advisor. Is that at overseas facilities, and here Mark and Ralph could possibly just indicate their impressions as well, is that once you are screened and once you are properly trained to use the equipment, which is very quick, it's an hour or two, all the instructions, and then you can run the experiments. Once that has happened, and the instrument scientist is convinced of your capability to drive the instrument and don't crash it and damage the 10 million detector or whatever, then you're your own. The instrument scientist steps back and you drive that experiment 24/7. And you have 24/7 access. Now at Safari, we've got a different environment that we're very rigid in our approach, that we don't allow visitors unescorted access into the reactor. And if we do allow that, it's very limited times. It's 1 week or 2 weeks. You don't want to do that for an extended period. But overseas, it's norm. People, once they also write an online radiation exam, radiation worker exam, where you physically have to go through all of these various options, understand the risks of radiation. But once you've done that, then you physically use that equipment 24/7. So that's something that we need to revisit, and that's what Dr. Adams was referring to as having this user-friendly environment for our users. Because Safari is running 300 days a year, 24/7, and therefore your users need to access the instruments 24/7 as well. So I don't know how we're going to do this, and we've had some discussions over the years with this course, but it's something, because I think you categorize it as a special person or something, but we need another category for our researchers. I don't know how we're going to do it, but it's something we need to consider. Okay, so that's very important. So, and then also, you've heard about beam size being done on peer review. So what you also need to establish is a program advisory committee. So Giovanna has indicated that the submitted proposals are sent to independent reviewers, and then they review the scientific merit, and then based on that, of a number, you possibly, I'm not sure, I couldn't remember how many reviews they use typically for each proposal. But let's say you've got 5 reviewers, and then ultimately you can then rank. How important is the science? Should this be accommodated? Can it be accommodated? And that call has to be made by an independent body like a program advisory committee. Of course, I think we're not yet at that position. That becomes very important when you're oversubscribed. We are not oversubscribed yet. But hopefully, from this interaction, there's going to be such a big demand for our equipment that we are oversubscribed by tomorrow, and we need to set up these bodies as well. Okay, then a very important aspect that we need to address, and I want to have Jitesh to drive this discussion point, is the establishment of a South African neutron scatter user group. No, sorry. Is it that? No, it's not that. So that's the other topics that we need to discuss, as well as the survey results. I just wanted to quickly show you what you entered as part of the registration process before the event, and then also just show you what we did an internal Nexa exercise where we looked at the various options of instruments, basically using performance of other facilities in the world, and we set up an options analysis where we basically identified a priority list of instruments, and just run that past you to show you. Okay, so the first thing, so this is a point I want Jitesh to run, is the establishment of South African neutron scattering user group. So this is this neutron scattering center, this whole framework. I started with a talk yesterday where I put a number of ideas forward that this needs to become a national entity as a large scale research infrastructure project, infrastructure facility. And we need possibly a different modality to run this. So at present, it's within Nexa, within the Nexa structure, but in Nexa's priority is commercial activities. This is not a commercial activity. So it becomes very difficult to justify not the existence of this, because Safari does, management does support the facility, but there are limitations, financial limitations and other limitations as well, which could potentially be addressed in a different way. So if this facility could be classified as a national research infrastructure project, and then name it something like a neutron scattering center or something like that, that is one modality, which I think Jitesh has very specific ideas on this, and it's best if he then leads this discussion point.
Okay, thanks. Yeah, so thanks, Andrew. Oh, Danny, Dr. Adam.
Yeah, thanks, colleagues. I mean, the first point is not on the discussion points here, Andrew, about the survey, but I have a serious problem. But if we can just go back to the previous slide, to say that people will start filling out the survey by telling you what instruments they want or needs. Imagine now here we have about, I don't know how many people in the room now here, active scientists, and they're all going to give you their wish now. You're going to set up with probably at least 25 instruments that they're going to have now, because they come from the different perspectives. And for me now, I can tell you now with the environment I'm coming from now here, and it, as Mark also indicated, yes, now it is currently these facilities are driven by people want to do the experiments, but we're working, I mean, because of the challenges on the fiscus, because of to be impactful, you have to narrow it down to things that's thematic and where you have geographic advantage and where you can be competitive in some ways. So I will mean, for me, the guiding principle should not be what instruments we need now, but rather that the colleagues or the researchers tell us what are the areas of that they're currently working in South Africa. I've listened now over the past 1.5 days now of the different areas that the neutrons can find application in. But some of the areas is for us almost a no-brainer to go at this point in time, given our fiscal constraint and the very small, in South Africa, I think our total research science base now is 27,000 researchers, for the entire country, compared to what you probably will hear what's in Europe. That's probably at one particular facility that you have those kind of numbers. So what I'm saying now here, we have to start saying what's the areas where South Africa can build a competitive advantage, where there is already capacity and capability in some limited way. And then based on that, to say, okay, these are the instruments that we can use now, because that will give you then a cross-section. If you start over the priorities to see if this is in line with, because people can come say, I want to do exotic science, and he will be a loner on that particular instrument. Are you going to invest in that? You see now, so you need to have an idea of what's the cross-cutting areas that we want to work in and pull our resources to be impactful. Short-term, medium, and long-term. Yes, hear what our colleagues saying from overseas, we have to be adapting to the times as well. But for us now, coming at this point in time, is first to try to go for the low-hanging fruits, where we have capacity and we have capability, and then building capacity and strength in it, and then slowly work into the next phase where we can venture into new areas. But for me, the thematic areas give us a cross-section of what it is now here, and then we can then from that extract from the expertise and from the overseas colleagues to say that this is the area that we have in South Africa we want to concentrate on, and these are the current instruments, because instrument development is also a dynamic environment now here. What's on the market now, for example, for neutron activation in terms of instruments, there's already maybe next generation instruments on the market now here. So how do you also keep in step with the time now here? So I think it mustn't be the hardware that dictates it, but it's rather the research agendas, again, the priorities that we have must set the agenda, and then we have to go to the market to say, what's the current instrument? Because you want to be current also all the time, because it's no sense in we buying old technology, because tomorrow, next generation. So if we want to come into the game now, what's the next generation, so that we can at least have a life cycle in terms of what we're going to do now for the next 10 years before we can upgrade and refresh our equipment. I think that will give us a current. So the colleagues must give us what we can do in terms of low-hanging fruits, We have the geosciences, the mines in South Africa. We have huge fossil finds in the country. You see now these facilities are doing work on South African samples. We should have been actually the country that was a leading country in fossil, analysis in our fossil finds. So those are the things that I think the low-hanging fruit that we can really pick now here and build our user base on that as we go along. But so I think, for me, I have a challenge with the way we approach this now here in giving me a wish list. I can tell you now, out of this room, at least 27 people is going to give you different types of things, which we cannot afford. As a country.
Thank you very much. Yeah, no, thank you. I think, we've also seen that the instruments are very versatile. So one instrument can serve most of the sectors here. So we're looking at versatility of instruments as well as the thematic areas that you speak about. And even if we were to motivate in our analysis about what instruments we think are important, etc., we're going to have to show alignment to thematic areas. And Mark touched on this in a bit. In Europe, the research was always driven by the users in terms of the science that they were doing, etc. But going forward, there's more scrutiny to these things being given by the decision makers, etc., to say, what are you doing in terms of the global needs, the things that the world needs right now? So we cannot escape what we need as a country vis-a-vis what is fundamental science or what people want to do on exotic things that you are talking about. I think let us first look at what people have put forward, Andrew, because we might find the two talking to each other and there's no debate.
Because what we have here is the regions of interest. So of course it's a very small statistical sample that we have here. I think the community is much bigger than the people in the audience. So what our assessment has shown, or what the inputs as part of the registration process has shown, is that is this as indicated here. So the biggest demand seems to be in engineering applications. Then we've got demand in energy storage and conversion materials, nanomaterials, crystallographic inorganic chemistry, catalysis, and magnetism. And you can see, so that is what the feedback from the results are. Of course, the important part is that we also need to increase the sample. I don't know how to do that. As part of this conference arrangement, we had a mailing list of 350 people. And our participation with this event was about 70 people in person and 25 online. So it's 1/3 of the people we actually approached. So I don't know how we reach the rest of them. So that's also I'm open. We are open for suggestions. How do we physically get more people involved? And the question is, would this sampling then change this area of interest? I can't make that call. It's something that we have to get back as a feedback from the community. So then we also had questions like familiarity with instruments. Do they have experience? Have they know about it, but have never used it? It will be applicable to research fields. So this is a very busy slide, actually. But what we indicated here is that, and you've heard this now a few times already with Mark and Ralph's discussions, is that the biggest demand, well, limited sample, emphasizing that, is neutron powder diffraction. You can see that one comes out as a very prominent. Then neutron imaging, as Ralph and Mark has indicated. Then single crystal, I'm quite surprised, but because I don't think we've got single crystal people in the audience. But of course, single crystal and powder diffraction go hand in hand. That these techniques are complementary. And then small angle scattering. So there's nothing new to what I think our international not advisors, but international inputs have also indicated. So I think we are getting a clear picture. I'm just not sure how representative this is. And the thematic areas that Dr. Adams is referring to. And then also neutron strain scanning. And so you can see, so ultimately there's a list of 22 instruments, and I agree, there's no way we can build 22 instruments. But this already shows a priority order. If we should decide on the first 5 instruments, there's a very good indication of what those instruments should be. And then the next step is then how do we link that to the thematic areas? And I think that link is already here. It's quite visible here because it was the same questionnaire that was used and the same inputs from our survey.
Andrew, it's a discussion. So, we also just go to the next slide. I think the one with all the instruments. Sorry. Is it? I was asking you to just go to the one with all the instruments. Okay. So there's an element here that's important, and I don't think the international speakers can see this, but there's a dollar tag attached to each of them. Some instruments like the neutron time-of-flight spectroscopy machine, that is possibly one of the most expensive instruments you can get. Whereas, I'm just giving an example, the prompt gamma neutron activation analysis, that is the cheapest instrument. I mean, with under R1 million, you can build that instrument. So we have to now weigh this and look, even though you only have a smaller number for the small angle, for the prompt gamma neutron activation analysis, it could be the first machine you build because you can build capacity, you can build, there'll be more interest for it, et cetera, et cetera. So it's a multi-criteria thing. It's not just only based on user needs, it's best value for money at the end of the day. If you've got 5 researchers using prompt gamma neutron activation analysis for R1 million, and you've got 1 user using neutron time-of-flight spectroscopy, which is about 50 million rand, you really have to think, or let's say you've got 20 users using neutron time-of-flight spectroscopy, but it's 10 times the price and unaffordable. So I think we have to apply our mind to this, but the list looks to me good. All the major instruments that were mentioned by the speakers are in this list. It looks like the audience and the people who are sitting and over the last 2 days, sorry, got the message. And I think we headed in the right direction. I think it looks very positive to me.
Well, this was actually pre-event. So
Okay.
post-event, we'll see if the picture changes
Okay.
or not.
Okay, I thought you're done. Okay.
Andrew?
Question, somebody, Tsepo?
Yeah, I just want to point out that we should also keep in mind that between now and when the decision for the instrument to be built is taken, this might have changed because the priority and the area of interest might have changed over time. And even the number of people who participate in this might have increased. In other words, we might have reached more people than this time around. So I just wanted us to keep that in mind.
Noted, Tsepo? Okay, so I'll just go to the other. So this is the instrument requirements, and that actually latches into what the previous 2 slides showed. And again, this is pre-event. So what we have here is the biggest demand, neutron powered diffraction. Then, of course, small scale structures. I don't know why that's that prominent. We have to go and have a look at who the respondents. I know Dave is a respondent, but I'm not sure who else were respondents in that process. Then strain scanning, then small angle scattering, and then imaging. So you can see it's the same sequence of instruments that are continuously coming to the fore, or the forefront. Then other services, so this now latches into what we've been discussing the first hour of this session, is the typical support services that are required from the community. And so, of course, access to specialized data software, analysis software, online user office portal becomes important, online radiation protection course, it's my comment of just now, chemical laboratories. So it's very important. So in many cases, your samples can be prepared in advance, but sometimes you have the need that you need to have a chemical lab close to your neutron beamline facilities so that you can do last minute processing before you physically put it in the instrument. It depends on the application, of course. Then 24/7 access, as I said, that is the norm internationally. Transport services to access the facilities. So Nexa is quite isolated. And students don't normally have their own transport. So it is a bit of a struggle to get to Nexa. And especially if you want to have 24/7 access, we need to have modalities. I know with the NPR, the on-site accommodation is one of the 5 primary activities. And this is clearly I think the reason has become clear over the last 2 days of why this is a requirement. An online experiment monitoring. Okay, that's something that I'm sure it can be done with all the 4IR technologies and things today. And it's like that at the international facilities as well. You can log into the instrument and physically extract your data or see what the sequence, how far your measurements have progressed and things like that. Of course, you can't change your samples offline. You have to go back and do that on the instrument. And then, of course, the deuterium laboratory. So especially in your biological sciences applications, the contrast between hydrogen and deuterium is very important, as many of the studies, many of the presentations have indicated. And that is a very special requirement. And at present, if I think from a neutron scattering perspective, I'm only aware of about 4 facilities in the world that have this linked to their facilities. So that is ANSTO has their own deuterium facility, ILL has its own deuterium, MLZ. The ESS, as Zoe has indicated, she already has a facility running without neutrons yet. And of course, the US would also have facilities. So possibly there are five, and I'm sure Japan would also have things like this. Of course, we can think about different ways of doing this. And we have got good chemistry departments and biological sciences groups in South Africa. And we could possibly link to Wits University's capabilities or University of Pretoria and have this deuteration done in their laboratories and drive the samples out to Nexa, 1 hour's drive, and you can put it on your instrument. I'm not sure if it's that easy. I'm not an expert on this. My discussion with Zoe, it's not always that trivial, but it depends on the complexity of the sample, of course. I must also indicate that, as you've seen, most of the biological applications are done with cold neutrons, and we don't have that at Safari. So that is also, it's an important consideration for the MPR, but moving forward to Safari, is it a requirement, or how do we physically address this? Yeah, this is very busy. So I couldn't summarize this. Let's just take the types of sample environments. So this is also part of the questionnaire: temperatures, magnetic fields, electric fields. And I must say, I have not made any conclusions from this yet. We physically have to go and look at it, but it seems that gas environments, so apart from temperatures, in situ gas changing environments is also important. So you introduce chemical reactions while you're changing the temperatures. And it seems that there are a number of atmospheres that become important. Now, just thinking about our X-ray colleagues, I mean, Esna, you've got your own facility where you can do different gas studies that are done at Sasol as a run-of-the-mill. Dave, you have a lot of in-situ sample environments. And I'm sure many of the X-ray labs in the country actually have that. Most have these Anton Power type of, well, you've got a much more fancy system than that. But most of these are commercial Anton Power type of environments. In the neutron perspective, it's something that Jitesh referred to the TC, Technical Cooperation Program, that we have for the IAEA. And one of our primary activities within that is to physically also develop this in-situ loading capability on our cryostats. Now, again, it's not trivial. It's a very, very complicated thing actually to do. And due to complexity, it actually is not a priority at present with our TC, Jitesh, but it's something we have to bring back onto the program. And that's something that we need to address, because as I say, our X-ray people are already doing this, and it's essential. I mean, Dave and Esna, you could possibly back me up here, or possibly provide further motivation of why such studies are important. And then, as I said, we did a next internal analysis where we physically looked at statistics of overseas facilities. We went and we looked how many publications at ANSTO, at MLZ, at PSI, at Berlin, has there been using these various instruments. And we also incorporated, so we made a map as well for the various thematic areas, which instruments could typically be used in that. So that was part of our options analysis that we did. And then we also looked at expertise. Do we have expertise in the country? People are experienced as users, and do we have the expertise physically to implement these capabilities at our facility? So our instrument scientists and capabilities. And here you'll see it's a very similar situation emerging. So we've got a list, as I say, of 22 instruments, and I don't know what the origin of that list of 22 is. I think it came from our previous pre-feasibility study. And as I said to my team many times, we'll never get 22 instruments. We need to prioritize, and that was the purpose of this exercise, is to prioritize and try to identify which are the high priority instruments. So I'm sorry, this is now very small, but again, you can see the same situation emerging. High resolution, high intensity powder diffraction. Okay. Neutron strain scanning, single crystal diffraction, SANS, imaging. You see it's the same theme in many different types of assessments we've now done. Pre-this mission, pre-this workshop, I think post the workshop, and then this is something we've done independently, purely basing our assessments on international facilities. Okay, Chitesh, that's what I can give.
No, thank you. So two of the key things that we wanted also out of this workshop is there's an international research reactor review utilization, okay, I forget the abbreviation. International Research Reactor Review. Yeah. So that's happening on the 21st to the 25th of November this month. And the IAEA expert review team, like I said, are going to be looking at beamlines and the potential, as well as make recommendations to us as to how we can go forward to improve utilization of Safari 1 and the new MPR in terms of beamlines. On one of the days, it's Wednesday, is it a Tuesday, the 22nd of November, they are going to be interviewing local users. They want a group of about 5 people who've used neutrons before for their work, users, and then about 5 potential or interested users. And we're going to have for the day a workshop, but nothing like this, but just some short presentations from the 5 IAEA experts that are coming down on neutron scattering, basically. And then there will be a series of interviews. Some of them will be one-on-one. Some of them will be in a group where you will sit down and talk to them. So we're looking at, we don't know if you want to show interest or raise your hands, or should we actually send out the call from those of you who participated. Andrew, I don't know how you want to handle it, but it's coming to that point.
I put it down there as a nomination of, so I'm not sure nomination, it can be you, that's a nomination, or it could be voluntary, of course.
Yeah.
But we need people to, yeah. So the review panel, just to, sorry to interrupt you, Jitesh. So the review panel, we had to recommend who we wanted on this panel. And I could just give a background. So the panel will be 5 people. So it's the IAEA leading the process. It's one of their officials. And then there's a person from the US whose idea this was. See, the person works at Idaho National in the US. It was his idea, Ron Crow. And so he will be part of the team. So Ian Nuno is the person from the IAEA. And then we had to nominate 3 experts. So the people we nominated, it's Dr. Rob Robinson, the previous director of the Bragg Institute in Australia. He's now retired. He established the whole neutron scattering Bragg Institute at ANSTO. He built it from a very low-key facility into a top 3 facility in the world. So therefore, it's very important that we have Rob with his inputs as well as his ideas. So the idea is that this panel need to come up with recommendations on how do we build our community, how do we proceed, how do we make this a viable entity into the future. The other person is Dr. Rob, I think he's Professor Robert McGreevy, previous director of ISIS, not a terrorist organization. He's from the Rutherford Appleton Laboratories. So both of these people come from very well-established research user facilities, top-notch facilities in the world. And they're both retired now. So both of them, I think Rob Robinson retired about 3-4 years back, and Robert McGreevy end of last year. And then we have also the person from the Argentinians are building a brand new reactor. It's called the RA-10 reactor. And they've established a body, a user group that they've established. And I'm not going to be able to pronounce that, but the acronym is Lujan, which is effectively the neutron scattering group with Argentina. And this lady is the director of that institute. And I can't remember her name, unfortunately. I'm very sorry about that. So she's also part of this panel. So you can see we also incorporated a person, which is in a similar process that we are building a community. So that's the way that the IAEA community will be. And for that, at some stage, so they wanted a lot of reviews from our side, which we've done scientifically, as well as Nexus strategic plans and things like that. but they also want to speak to the stakeholders. And that is the reason why we need two categories. They specifically asked for two categories of experienced users. So experienced user would be a person that has used South African facility or any facility in the world. I would prefer if actually if it's both, it will be very good. But both perspectives are essential. That the review panel can see that we do have a very strong cohort of users. It's a very small community, but we do have a very active community. And then the inexperienced users, inexperienced stakeholders. So people that are new to this, who first heard about this last few days, we also need to get their perspective. The panel actually wants that perspective, it's not us. So it's just to add what Jitesh was saying.
Yeah. So I don't know if we can have nominees now or we open it up. We open to anybody who wants to submit their name. If you want to do it by email, I see a hand already going up.
Who's that? I didn't see it, sorry. Okay, so we've got Dave. Please send me an email with your contact details. And from paleontology, very important, and that links into the thematic area, as Dr. Adams has indicated. Dave, he is very important. Esna, from the industrial perspective. And you've used our facility as well as Grenoble in the past. So I think your inputs will be extremely valuable. Aleta, don't look down. Got eye contact, Aleta. Or Charles, it doesn't matter, or even Susan. I mean, we've all been users at Ansta. You've also used our facilities at Nexa. I think your inputs will be extremely important. Chache?
Our geosciences colleague over here.
Wait, sorry, I'm missing
right in front. At least 5 of each. Yeah. Yeah. But we already have some now. Yeah. So we can also. Yeah, they can also.
Yeah, please send us to the SA-SENS email address. Send your ideas and nominations.
Yeah, we will send an email out, I think, to everybody who was party of the workshop, because having someone who was not here, whether physical or virtual, will make it difficult at that point to be able to answer. If we don't have the numbers, then we will open it up. But I think let's try and restrict it to those who were present. At least there's some basis and background. And then the second thing that I wanted to push and maybe just plant the seed in your mind. I know Andrew is very nervous about this one, but most of the time this was driven, and neutron scattering was driven by Nexa, and Nexa's mandate, as Andrew has said, and I don't want to speak on behalf of Nexa, but is primarily focused to nuclear research and development, and the particular word there is nuclear research and development. And neutron scattering itself is not on nuclear research and development. It's a tool that is used in a broad variety of areas. And if you look at the presentations we had over the last 2 days, how many of them spoke about developing a fuel pellet for a nuclear reactor or anything? None of them. So sort of what Nexa wants to do, and the idea of Nexa is to make the facility available to the community and to users to be able to do research using nuclear techniques. This is the fundamental thing. So, but the way I'm seeing it, and from my experience and what I've seen, is we need academic champions, somebody who's not at Nexa, who's going to champion neutron beamlines in South Africa and take it to the next stage, to say, be able to talk about neutron scattering, be able to talk about how it helped them in their research, someone who's going to be able to bring the user community around, etc. And I know it's a tall order, and Andrew's always telling me, but how are we going to incentivize them and all of these kinds of things? So we have to work out those modalities. And if there's ideas from around the floor on how to make this work and how to make it, of course, we can put something together and present it to you. I was in the process of drawing up some kind of terms of reference, but I said, that's like pushing something down someone's throat and saying, eat it. It's better if it comes from the floor, because we want it to be driven by industry and academia and those kind. It doesn't need to be the same person for 5 years or 3 years or 2 years. This thing can rotate. but to establish some kind of user community and people who will actively pursue promoting the facility, the instrumentation, etc. And we don't know where this will happen and how it will go forward in future. So we're not in the chicken and egg situation. I don't think so let's just look at the chicken and the egg. The chicken is the instruments all operating and running, and the egg is the user group and the people who are using it. And it's not a binary situation where we say, which comes first? Do we build the instruments first, and then the instruments can lay the egg, and the egg can hatch and all the users will come and use it? Or do we first get the egg hatched to become the chicken? So it's not like that. I think it's going to be a parallel approach, and we have to, I think the egg is already laid. I think we have to incubate it, and because the chicken is a couple of years ago, the really big chicken, and we need to incubate the users that we have, the potential users that we have. We have other facilities that users can get access to and use and incubate and grow our user base so that when the chicken comes and it's fully fledged, we have everything working seamlessly. So that's my message, Andrew. I don't know if I've covered everything. Questions?
Thanks to this for that. I think two contributions I would like to make now. The first one is that we have seriously have to address the access model or the location of this facility in Nexa. If the status quo is going to be the same as it is now, it's going to be a big challenge. We're supporting now, I mean, one of the programs I'm supporting is our collaboration between South Africa and the Joint Nuclear Institute in Dupne. And there's a big group at UWC and Stellenbosch that's using neutron activation to look at environmental studies, the mussels, around the West Coast and stuff like that. And they complain they had to pack their samples and go all the way to Dupne in Russia to do their samples over there because for the simple reason they could not get access to Nexa for neutron activation. So we have to, I think that will be the huge limiting factor if we don't kind of address that, to isolate that facility from the next broader scope of work now, so that is an open access, because it's going to be funded by public money. So that means it must be openly accessible to any researcher in the country without constraint. I mean, it took me, I was only there Nexa once in my lifetime now, and it took me an hour to get from the gate to where I want to be. So, I mean, that is unacceptable. I mean, researchers, don't have the time, but it's just, discouraging people to jump all those hoops and just be on the premises and all the time having a bodyguard around you now. The independent usage is compromised in that. So that's the first, thing I want to recommend. So that's a serious thing that needs to be tussled between the MRE and Nexa as part of the model for the implementation of this, or establishment of this facility. The other one is that this MPR is going to come in 10 years' time now, but we have already activities that's going on now. We need to build up the community over this period of time. And therefore, I think we should use our international facilities like we have now here, our international partnerships to build now, the community. So when that our instruments are on the commission now here, we have already a well-established user group now, because we cannot start in, because we have, we started the work with ESSS. You have been assuming good friends at ILL and in other, so I think between DMRE and DSI and whoever now is supporting research, the NRF research in it, is to start a program, to support the researchers to go overseas, and especially the younger generation, to get the training now, so that, because the growth is not going to come in our established researchers. These people are retiring, so the community will actually decline if we just work on what we have now. It's the next generation that we have to invest in, our postgraduate students, and there's opportunity to use our international bilaterals to go to these facilities. Our colleague from Germany said there is an agreement with Germany, so people can go there. We have an agreement with GNR, where the people can go, and other facilities. Now, so I think the opportunity is now to use actually why we do this build up now, to get to the, I mean, the final system, to build expertise now here using our international collaborations.
Thank you,
The
Dr.
second
Rams.
point now, yes, we have to address seriously.
Yes, that is why
The nexus problem, and use this interim period to build capacities by using our international collaborations.
Yes, that is why we have that framework that we are developing that has an implementation plan, and hopefully in the next couple of months, we can get it at least approved at the Nexa level, and us as DSI and DMRE and Nexa can formulate the way forward and expedite this. And I've already had good discussions with Mr. Mayoli, Dr. Ramprasad, and Jan Reinzifa, Dr. Professor. And it seems like we can unlock a lot of things that are currently not being unlocked, and things that Nexa are looking better as well in terms of being able to do that. And the impetus of the MPR is also putting pressure on this. So, you know, there's one thing about being able to access, and I think that feeling of being at a nuclear facility, it has to be there. So when a researcher comes there, he feels privileged to be able to do his work. But it mustn't be to the point where he's not felt welcome. He must feel welcome and say, you know, I'm welcome here. I'm privileged to be here, kind of thing. Not, okay, please don't come here. You're just hampering our security. And I think that's the kind of thing that needs to change and get adjusted. Because I struggle to get onto the Nexa site, and it's because of the security. It is a strategic facility, and it is something that the world is keeping an eye on us, because unlike some other facilities, we have high enriched uranium on the Nexa site as well. But I think there's ways of addressing this. So I don't know if there's any other comments from the floor. Thanks.
Could I just add, so if you look at the second group of items I've got there, the more active academic involvement in growing this community. So I think while we've got people around, Giovanni, I'm very pleased you putting up your hand. So we need to think, how do we get academia more involved in our facilities? I just listed a few. So hands-on practicals at Safari. That's one thing. We had some programs in the past, but it can be reinvigorated and we can get much more active involvement. And that's one way to spread the message and create your users of the future as well. And then, of course, inclusion of neutron scattering in coursework. Now, unfortunately, I see Dave has left, but I had discussions with Dave, but Giovanni and Aleta, and all the people from UP, this is something we need to consider as well, because that's where you plant the seed. If this is part of the coursework, then this unfamiliarity with neutron scattering techniques, that disappears. If you do that, you plant the seed with the academia, and supposed to be students at honors level or somewhere there. And I know discussions with Professor Pastorius as well. You mentioned that some universities have a program in experimental techniques, which basically informs students of different techniques, SEM and all the other techniques. And of course, neutrons can form a very integral part of that as well. But we need inroads into the university system and university coursework, you know, engineering departments and your sciences, physics, chemistry, geology, all of these departments, that the seed is planted very soon in the careers of senior students. And it's open for other suggestions as well. So Giovanni, you wanted to add something?
Yes, Giovanni from UJ. ILL has Giovanna, and we have Giovanni here. Yeah. In any case, this issue of increasing the user base has come up quite a lot. And I guess you'll have a meeting like this in a couple of years' time, and you'd like to see this room full. And I'm wondering if you have a plan in place to increase the user base. For example, do you have open days at Nexa where you bring in school kids to excite them about the facility? I've been very involved in synchrotron work, and what I've always noticed at the synchrotrons is that they have these open days and they bring schools in. I think it was mentioned by some of your overseas guests. And this gets the youngsters excited and inspired. So I assume that you have open days at Nexa where you bring school kids in. It may not be because of this security situation. but you've got to get that to change because you need to grow, you need to inspire the next generation, emerging researchers. And the way you do it is, like you said, you took the words out of my mouth, planting the seed in these young minds. And the other thing is, do you have in mind conducting a roadshow about the benefits of neutron work? There will be user meetings every 3 years or something like that. But the difference for me between the neutron case and the synchrotron case is that we don't have a synchrotron facility. We've got to go overseas to use the synchrotron. Here we have a working facility. You can show it off to these young minds and get them excited and inspire a certain percentage to move in this direction. If you have these road shows at the various universities, I'm pretty sure that you're going to get people in the life sciences quite excited about the possibilities. Okay, like you pointed out, doing this deuteration seems to be very sophisticated, but they could be learning the technique from you and then accessing overseas, or like you said, you could set up such a facility at one of the universities. So, as I said, what are you doing to ensure that in 3 years' time, when you have a meeting like this room is going to be full?
Yeah,
thinking aloud.
It needs to become a what's right word, dedicated program to do that actually. But Giovanni, Joe, also, how do we approach the universities to get this into the coursework? I think that's also something that we need advice on how can that be realized. I know we're going out of time.
Dr. Adams had his hand up.
Dr. Adams, sorry, I didn't. Chris, I know your hand is also up. No, not at all.
Not at all.
Okay, Chris, if you can go first, you've got a mic. So.
Thank you. Just to clarify the point of access control at Nexa and Safari 1, with respect to Nexa, it's a national key point, and there are regulatory control and the regulations we need to comply with. However, if you are a user that wants to access Safari 1 on a routine basis, we can do a screening. You do a radiological protection course, and you can have an access card which you routinely can come on site without a problem, and also access Safari. Of course, if you receive the induction and the training, you can work in the Beamport floor, on the Beamport floor without a problem. But you need to comply to the regulations and the procedures. That is normal for any facility. If you are a user that is coming once a year for 1 week, that's of course a different story. I mean, then you need to go with your ID card, etc., and access will take you about half an hour or so. Once you get to Safari and we have access control permit system, we give you a permit and you can access Safari under supervision, of course. But routine users, and we have people who are routine users, which we issue an access card, and then they can access the facility 24/7. Of course, security in Safari was upgraded the last 8 or 10 years. So we can have people coming in and work if they needed to do, and they have a routine access card on a 24/7 basis if they like. So With respect to the open schools and open days, at Safari before COVID, of course, we had about 2,000, 2,500, and I've done the statistics just a few months ago. 2,500 private people or public people that is coming to visit Safari. And we give them a presentation. So we are open for presentation school groups. Of course, you need to be older than 18 to access the radiological areas. But we do have universities and other groups that's visiting us. So, and it's normalizing now again after COVID. So I think we can move to that next step, which Dr. Adams is requiring. So I don't see that we have a problem with respect to that. So thank you.
Thank you, Chris. Dr. Adams is.
But the question about universities,
To get universities involved, yeah,
Coursework.
Yeah, there could be some modality to
yeah,
get
I'm not
inroads.
in, I mean, I used to be in the university system, so probably, I mean, professors in the room here were currently in the university system, but the thing is also, I mean, you cannot introduce any courses in university if it's not feasible. There must be demonstration. There's a demand for the course. Remember, the universities receive their subsidies based on the number of students that pass these courses now here. So you must demonstrate that if you want to introduce your course, I mean, there's enough students for that. But you mean the modality that we be using in some cases now here, that there are existing programs that you can say, can we bring specialized courses into an existing program? That's doable. So when there are credit, where you can have credited courses or degree programs, or just mean starting specialized courses into an existing program. But those things are all doable. I think that we have to find the warm bodies to do that. That's and I think just mean while I'm in the mic now, Andrew, is that the whole idea of champions is very important, because if there are not people that's passionate about saying nothing's going to happen. We found it with our South Africa Research Infrastructure Roadmap development now here, which was a huge project. We had champions in those particular areas that was now organizing the entire country. And it was a requirement that when you bring a proposal for that facility to be established, you must demonstrate that you had consulted each and every researcher with an interest in that particular field. Otherwise, we're not going to pass that now. So it was regional, national workshops. This was conducted where they bring people together to brainstorm that. That's the only way you can get a message out to that. So, and a lot of other groupings now use actually of institutional champions. There's, for example, the American Exceed program, which means trying to promote high performance computing. And they have champions in the particular universities now here, which can then assist with either in-house workshops or workshops within that particular region now here to championing that particular. So institutional champions, but a champion must be something a voluntary purpose. You can't say, I want you to be a champion. You must put up your hand and say, I want to be driving that now. Thank you.
Thank you, Dr. Adams. Tebo? I think Ms. Pistorius?
4 o'clock.
Yeah, so I was just going to ask, I know that there is some diffraction course at the University of Northwest. Is it possible that this thing can be done along those lines, or maybe the other institutions that need to be approached can be approached following the same model with the Northwest University?
No, I can't answer that. So.
You know,
There's a lot of hands now. I think first was Professor Pistorius.
Thanks. I'm in metallurgical engineering, which is, per definition, a small engineering department. But I recently saw the figures of a total number of masters and PhD students in engineering at the University of Pretoria. And the ratio of master students to PhD students is about 5 to 1. Don't quote me on, but it's in that order.
you know. So I think the prime market is probably a master student and not a PhD student. You'll get more bodies. The dilemma with that is that there's significant time pressure on a master students. You know, he or she typically has about 12 to 18 months worth of experimental work. And I would think the way to get a bigger involvement is to connect to supervisors, because, you know, because of the time pressure and because universities are becoming more institutionalized, or, you know, there's an attempt at stricter management, whatever cynical way you can phrase it, is that, you know, a lot of the work is driven by a proposal and a definite research plan, you know, and I'm using that system. So, for example, for a master student, there's an agreement maybe 6 months or 9 months ahead, but at that time you have to attend this conference and have this work ready. So, and that is, well, those decisions are made early in this time scale. You know, there are exceptions, but typically fairly early in the project planning for a master's, and let's focus on the master's, you know, the project is defined, or 80% defined. And I think the way to get neutron scattering into more master's projects is to connect to supervisors. And, you know, you can probably, you know more about it, Andrew, than I do, but it's probably the sort of users are in the metallurgical engineering departments, the mechanical engineering departments, possibly. And in you know, I speak from an engineering perspective, and probably in chemical engineering in most cases. You know, so if you can, you know, target those people, and those are probably, if you look countrywide, that's between 10 and 25 people. You know, if you go and talk to them with specific examples, I think you'll pull many master students in relatively quickly. And from that, the master students normally, some of them go on to a PhD, you know, when the marketing was done for you by that point.
Thank you very much. Of course, you know, if we can do it, if we could have the awareness session, let's say at honors level or fourth year, then the student can possibly push that with their supervisor. So that's also a different way of doing it. But thank you very much. Isna?
Okay, a few things.
You can introduce yourself. I think it's the first time you're speaking. Is it? I can't remember.
Isna du Plessis from Sasol. So I'm looking through catalysis lenses. A few notes, and I completely agree with what Prof. Pistorius has said. Even in terms of a PhD, 3 years is quite short. So for the student to have one unsuccessful application for beam time and to have to go through another 6 months and wait to get beam time possibly, and to finish in South Africa's unique 3 years of completing a PhD is an extremely stretched target. Now we're sitting, we have such meetings as well, but I mean, we all sit around and someone should. And I mean, Nexa is strained in terms of champions, you know, doing the best they can, but you can do so much per person. The same thing in terms of the academics. They're already overstretched. So we all sit around and we say, yeah, that's something we should do. I feel that we should have at least one center of excellence and a funded person with the main job and being held accounted for it, for spreading the news on neutrons. And it's not only the talks about it, but I mean, I had to go through a similar process at Sasol. I had to be a synchrotron and neutron nut to convince management to put funding to it and basically to convert them to understand what you can get from that. And you need a neutron nut to drive this nationally. Someone with a main focus to do that. Another thing in terms of, I won't use too much time in terms of trying to change the teaching material at undergrad. Students are wonderful things. They learn from a supervisor and from their fellow students that successfully use the technique in the blink of an eye. So I think in terms of our current situation, And I can understand that students are struggling for the basic bulk characterization technique results in South Africa. I'm a mentor at University of Fort Hare. It's one of our previously disadvantaged students. And some PhDs were delayed because of samples being submitted to centers of excellence and results not being received on time. So there's a lot of fundamental group groundwork to be done. And then the higher end techniques is the icing on it, and having our PhDs and master students at world-class level. And that's done through supervisors at university that has already active research programs at overseas facilities and already utilizing what we have at Nexa for the basic start of characterization. Then putting on my SASOL hat, and I will shush now. Bulk characterization, done. Bulk characterization under in situ conditions, done. But in terms of catalysis, we're talking about the surface. That's where catalysis takes place. And that is really the advanced step we're looking at. So full support, yes, we need high resolution bulk characterization techniques. I fully support the prioritization that I've seen from the studies that you've done. And then the step beyond would be surface characterization techniques. Now I'll shush.
Thank you, Esther. Joe?
Sorry, are these flat surfaces? Sorry, Esna, are these flat surfaces or spherical surfaces? Okay.
Then you need vacuum then. It's just about, you mentioned about making inroads to the universities via courses and so on. And, you know, that may have a problem, as Danny was pointing out. Setting up a course, well, you do that by approaching the head of department and so on. But at ESRF, they have this Hercules school where they conduct courses in spectroscopy, diffraction, excellent courses. So maybe you should think of running something like that, you know, the Hercules school. You run it at Nexa over 2 weeks, and you invite students in, postgraduates in, school them in diffraction and neutron work and so on. I think that would work quite well. Okay, you've got to think about the logistics, so on, but instinct tells me that that's the way to go.
Yeah, thank you, Joe. So yeah, the Hercules course, of course, is a very well-known course. And I think it actually runs over 2 months or something. It's a very extensive course. And they involve many of the European facilities. Neutron facilities are also part of that overall process. And we should actually consider sending South Africans there, getting new blood, you know, not this. If we train people, it's the same inbreeding, same bad ideas. Whereas if we have people trained in that Hercules course, it will be fresh, new, bright ideas as well that we bring to our perspective. Yeah. Yes.
As a bridge.
Yeah. Yeah. Yeah, so a point of departure is that hands-on practicals. You know, that's the first point. We have a practical of 2 or 3 days, and you plant the seed, and then it builds to what you are proposing, Joe. Yes. Yeah. Yeah, most of them run these winter schools and summer schools. Yeah, you have sent the student. Okay. Thank you, Joe. Susan?
Hi.
Introduce yourself.
Susan Jacobs from UJ. At UJ, we have a postgraduate school. So like many of us have mentioned, academics are stretched. So maybe you can access the postgraduate students through the postgraduate school. And with regards to having masters and PhD students, I think as Dr. Esna said, they're very stretched for time. So I think you should introduce them at a 3rd year level. And in our group, that has worked. We introduce them to mini projects in their 3rd year, and then they get interested in the subject, and they carry on with honors, masters, and PhD. We've got 2 students in our group who are following that path. So mini projects during recess at Nexa, also for honor students, that could also work. I think the challenges we faced in the past, and Prof. Prinsloo can attest to this, is access, getting access for students to Nexa, transport to Nexa, funding to get there. So if you can work through maybe the postgraduate school at UJ, I don't know, maybe you can get through some of these things. I don't know. Thanks.
Yeah, in the past we had this hands-on courses with the Professor Aleta, Professor Prinsloo. I'm not sure if you were part of that, Susan. I can't remember that far back anymore, actually.
Yeah, I did bring students, but
But it was a process, as you
Yeah.
yes, because you have to travel from Johannesburg. It's a 1 hour travel or 1.5 hours, and then getting access, and
yeah,
very quickly a day is dispensed in different activities.
yeah. But
And
I think you should start off with a very basic workshop across all disciplines in science, without those big equations that are intimidating. Just a very fundamental understanding, and then give them the opportunity to come and do something hands-on. That's how they get over their fear of touching instruments and working with science. Yeah, thanks.
Thank you very much, Susan. Okay, I think we should start wrapping up. We're 20 minutes over time now already. Anything final from your side,
No,
Jitesh?
I'm fine. Thank you, Andrew. I
Fine.
think it was
I'm not sure,
informative.
online participants, are they still there? Mark and Ralph? They're still there. Mark and Ralph, you've been hearing our discussions over the last hour or so. Any last minute comments, suggestions from your side before we wrap up our proceedings? So Ralph, you're on the full screen, so you could lead the way, please.
I think we had now more or less mentioned all the issues. So I think we had a broad and long discussion about all the fields. So I have nothing now particular in mind what we are missing, or I think we have touched all the issues.
I agree. I think you've done a really good job, and you really have covered all of the ground. I've only got one suggestion to make. You're emphasizing already the need to sort of reach out already to more people, and I think that's absolutely right. And I just wonder whether you have learned societies in South Africa, for example, in physics, chemistry, and so on, and you can use those to try and reach a bigger audience and attract more people towards your initiative. So that's the only other thing I would add at this point.
Okay, then in wrapping up, I want to thank both of you for your interest in this event of ours and supporting us to a large extent, and for your expert inputs that you gave and your very good presentations yesterday and today.
Thank you. You're welcome.
Thanks.
Okay, so then I just want to thank everybody here for your participation. I think there's a word of thanks by Pradesh, but it's very important that we engage and have discussion, and please feel free to communicate and send an email or whatever is necessary. Ayana, are you doing the, oh, sorry, I got it wrong. So thank you very much for your participation.
Thank you. Thank you. Ladies and gentlemen, as we close, I also want to utter some words of thanks to you all. I really on behalf of the CEO of Nexa and the executive committee, would like to thank all of you for having taken your time to be here over the last 2 days. We do appreciate that. I want to really believe that from this workshop going forward, we will take our level of engagement with the user community to another level. Not just in terms of numbers. I know we are a little bit disappointed with the numbers, but not just in terms of numbers, but in terms of quality as opposed to just quantity of what we can get out of this opportunity that our multi-purpose reactor will bring. And I really would like to encourage you that you take advantage of this opportunity. We are really excited about this project, our multi-purpose reactor project. I just want to thank a few people. I don't want to leave anyone out. First and foremost, I would like to thank our international speakers for the excellent sharing of knowledge and wisdom that they did with us over the last 2 days. It was of course, mind-blowing. And some of us got lost through the expertise that was being shared. But nonetheless, it shows this is world-class work that we're talking about, indeed. And I would also like to, let's give them a round of applause. Really appreciate it. Thank you, colleagues there. I would like to thank the team that consists of NECSA, the TSI and DMRE that have made this event possible, well supported by Madam Tesha there. I can't mention each one of you, unfortunately, but let me mention Dr. Fenter, Mr. Kesho, Dr. Adams, he's just left, representing in the main and taking a lead, within those organizations to ensure that this event was a success. Thank you very much, colleagues. And I do have other names, so just like to mention, of course, Uchachi and Robert and Dion. But look, colleagues, I can't mention all of you by name. I think it was a team effort. So whoever I did not mention by name, we appreciate you as part of that team. Let me also thank the NECSA and DMRE media team, well led by Amelia and Tabani. I think they are just outside in the foyer. Thank you, Dr. Pratish Rampesat, my colleague, GE of Research and Innovation at NECSA, for your continuous support for this event that we've just had. I thank the session leaders, all the session leaders, for the wonderful way in which you have led the different sessions over the last 2 days. And thank, of course, the Lake Hotel for being such good hosts for us. All the participants were here. Ladies and gentlemen, you can give yourselves a round of applause. Yes, indeed. We look forward to our Aero mission, as Uchitesh mentioned, towards the end of November. Thank you very much and have a good weekend. Thank you.